Welcome to the workshop, ITU workshop on machine learning for 5G, for future networks, including 5G. The workshop is associated with the new focus group on this topic. Sorry, just there was an accident. and wait a minute. I have to. Sorry for this. So welcome everybody. I hope you had a good trip. Also, welcome to remote participants around the world. And so we have today. This is a workshop. We have a series of excellent speakers here. We organized the workshop into 4 sessions. We are starting with the first session, like in 5 minutes, and then we are going to finish around 6 p.m. And so I think that that's it from my side. I will just give over to Reinhard. He will say some words about logistics and also introduce the IT2 director, Cesar Lee.
Okay, good morning. My name is Reinhard Scholl. I'm with the ITU Secretariat. Can I just have a show of hands? Who's here for the first time? Oh, okay, quite a few. All right, so just some logistical remarks. You can also listen to the presentation using those earpieces. Yeah, and you'll figure out how this works. There are not too many permutations here on the buttons. If you ask a question, would like to ask a question, just raise your hand, and when given the floor, you click on this green button here, this big one, and then the red light turns on, and then people will hear you. We have remote participation. Quite a few have signed up for that, so we may have questions coming also through the chat box, and we have a student from the University of Geneva who is monitoring all that, and then he will convey the question. The PowerPoints will be available during the day as speakers speak. There are a couple of those who didn't wish to have the PowerPoints be made publicly available, so we'll respect that. The cafeteria is you go out and then right, and then about 30 meters or 40 meters, it's in this other building. There is the cafeteria, but there are also restaurants around out here. And the bathroom is also located there. Then perhaps we should maybe point out the moderators of the successive sessions so that the speakers can get to know the moderator and then just discuss a little bit the session. So if I could just have the moderators stand up, so that's Wojciech and Kim and Songbok. Songbok, if you just stand up so people can see you. So those are the moderators of the successive sessions. The first moderator of the first session, that's Slavomir. So if in the coffee break the speakers just go to talk to their moderators to discuss the session, that would be good. And then if you would like to be interviewed, if you'd like to say a few things, we have an interview corner. I guess we do it here or outside, yeah. And my colleague Fred, that's our communications guru here, he will take care of you. So if during the day, coffee break, I guess preferably, and perhaps also during lunch, you would like to be interviewed, please contact Fred. And I think with that, I have done all the logistics part. Now, you would like me to say hi, introduce you to Cesar Lee. So Cesar Lee is the director of the Standardization Bureau, and he is in Vietnam right now, but he's going to say a few words to you from Vietnam. And now we will see Cesar. Okay, Cesar.
Hey.
Floor is yours.
I hope you can see me. Good morning, everyone. Let me welcome you all of this workshop. we are still in the first month of January. In particular, we are before the Chinese Spring Festival, so it's good enough to say Happy New Year to you and your family. I have to start my apologies. I could not join you at Geneva. I'm out of my office. However, I believe this workshop will conclude fruitful results with your contributions and active participation. Let me introduce ITU shortly for those who may not be familiar with us. ITU allocates frequencies to services that make use of wireless spectrum. So 5G spectrum is one of the critical parts for us. We also develop standards. Few of examples of our standard is your country code, whether this is a fixed phone or mobile phone, or broadband technologies like SDSL, optical transport, and video coding such as the 8.264, 8.264. The ITU also assists developing countries in setting up their ICT infrastructure. I was at the Consumer Electronics Show this year in Las Vegas. The buzzword number one in CES 2018 was AI, followed by the topics of 5G, self-driving, smart home, smart city, augmented reality, virtual reality, sports, well-being. So we found 80% of the topics at the CES are topics that ITU is working on. So therefore, this workshop and the creation of this focus group on machine learning for 5G are coming at the right time. I saw last week, KT, Korea Telecom, already used machine learning for their network management. The workshop serves as a prelude to the focus group meeting. The goal of the focus group is to draft technical reports and specifications for machine learning for 5G, addressing network architectures, interfaces, protocols, algorithms, data formats, as well as standard ecosystem, specific use cases, and their standardization questions in relation to 5G. ITU organized last year the first AI for Good Global Summit. Its goal was to examine how AI can help achieve the sustainable development goals. Some of the world's top AI researchers participated at the event. I would like to invite you to the second version of the AI for Good Global Summit, which will be held at Geneva from 15th to 17th May 2018. Taking this opportunity, my thanks due to Focus Group Management team under the leadership of Professor Slomir Stanchak, Fraunhofer, who put together this workshop, and thank you to all for having joined this workshop, either by coming to Geneva or by participating remotely. Again, I could not join tomorrow, the first focus group meeting. This does not undermine ITU's interest on this issue. I'm so pleased to introduce Dr. Reinhard Shaw, Deputy Director of TSB. He serves as a counselor of this focus group. Having said that, I wish you have a good success for the workshop and a joyful stay in Geneva. Thank you very much.
Thank you very much. Okay, so the questions maybe? Oh, okay. Okay, so now I think that we can start with the first session. And my understanding is that the speakers of this session, I mean, the session is use case on applications, and yeah, he's gonna, yeah, I know. I will just moderate this this session. And my understanding is that the speaker should come to me here. We have here 4 speakers: David Gisbert, Ahmad Al-Assad, and Yong Going Hong, and Xiang Cheng. David, you are here. Okay. Okay. Thanks. Yeah. Just we are starting with a first talk, which will be given by Professor David Gisbert from Eurocom, so not so far from here. And the title of the talk is Machine Learning for Decentralized and Flying Radio Devices. So as I said, we have like 20 minutes for the talk, and then 5 minutes for the questions. So David, the floor is yours.
Okay, thank you. Everybody can hear me? All right. Thank you. I want to thank Slavomir and the other organizers of the workshop for this first opportunity to come to Geneva for the ITU for this interesting topic. So, as you can see from my presentation's title, I'm here to tell you a little bit about some new, maybe sometimes unconventional scenarios of application of machine learning in wireless communication systems. So let me say a few words about this. First, let me, I'm always asked, what is Eurocom and where we are? So let me just say 2 words about Eurocom, my research lab. And since we are not very big, we're quite small. We're located in Sophia Antipolis in the south of France, in the red dot, as you see there. It's about a 1-hour flight from here. In Sophia Antipolis, which is a big technology park in France. We are a research lab completely focused on ICT topics and with English as a working language. And it's an example of the shared economy. We are owned by a number of companies and universities in Europe. These are our shareholders, and I give you a few examples here. Institut Mines Telecom in Paris, TUM in Munich, Chalmers, Polytechnique de Torino, etc. I'm not going to list them all. And this is a picture of our campus. And you will have the opportunity to see the campus from close a bit later. I will show you a live demo of some experiments we are doing there. Going to the main topic, since this is the use case session, I thought I should take a few seconds to describe what I think are in the broad sense, the set of potential applications of artificial intelligence in wireless networks. This is not a full, complete list. These are just a few examples. Let me start first by explaining why we think, at least in my group, machine learning has a potential to change the game in wireless networking. You probably will agree with my points here. These are widely accepted reasons for why machine learning can be useful in a number of applications. I would say the first one is about the need to be robust with respect to uncertainties, especially in the modeling the physics, which can be hard sometimes when you're dealing with wireless networks. The second one is the ability to exploit a large number of measurements that are done routinely by radio devices. And the third one is the ability to use efficient implementations of these tools. So where are potential areas of applications? Well, I just listed a few examples here. First, at the lower layers, in terms of modulation detection and classification, performing error correcting tasks at the transmitter and receiver, searching for the right beams when it comes to massive MIMO setups, You have a number of applications of this kind. I will give you another one a bit later on. The link layer, people talk about traffic detection and classification, improving resource allocation using predictive methods. Another one that is more at the system level, optimizing the parameters of software-defined networking to be able to cater to a number of very different traffic classes of traffic and user requirements. And then we hear more and more about quality of user, quality of experience enhancement by using user-machine interaction. So today I will tell you a bit about something a bit different from these scenarios, and so I call that new perspectives. And I will take the perspective of trying to deploy a network of autonomous radio devices. I'll explain a bit more what I mean by this, but the goal will be to try to deal and be robust with respect to uncertainties in a number of ways. In particular, uncertainties in the measurements that are done by the radio devices. So the fact that there's noise, the fact that there's limited feedback capability. And also dealing with decentralized decision scenarios. And this is particularly useful when you want radio devices to cooperate with each other. And I'll give you two examples. The first one is called Team Deep Neural Networks for Cooperative Decentralized Communication. And the second one is machine learning for optimal placement of flying relays. And the common part between these two scenarios is the fact that I'm dealing with radio devices that have to make robust decisions on their own and do not want to rely on cloud centralized decision process. And we believe machine learning can be quite useful in this type of scenario. So the first one is about decentralized wireless networks. So imagine a wireless network that is composed of devices that cannot rely on an optical based backhaul, because typically they are light equipment or low cost equipment or mobile equipment like antennas that are mounted on light posts or trams or cars or drones. I'll come back to drones a bit later. And then you want those equipments to cooperate in order to extract the maximum possible efficiency from the network. So it could be cooperation in terms of resource allocation, interference management. There's a number of ways that these devices can be made to cooperate. I'll give you a small list here. So the key thing is the fact that because there's a lack of efficient backhaul here, those devices have to rely on mostly local observations in order to make cooperative decisions. So if you're dealing with a power control problem, power control is an efficient way of cooperation between devices. But if you have to decide on your own which level of power is optimal to use in a network where you don't really know what the other devices around you are going to do or how they're going to behave, this is very challenging. So we think that AI here or deep neural networks can be an efficient way of being robust with respect to noisy observation and local observation. And another key thing is that I want to be able to predict the decisions of other devices around me in order to come up with the best decision for my own device. So the concept we have tried here, and there's a paper that's been proposed a few months ago, is denoted here as team DNN. So it relates to the framework of team decision, which is a branch of game theory where the players are willing to cooperate and they are willing to maximize a function that is based on the network performance. They're willing to improve the network performance. They are not egoistic. They are not conflicting in the sense they are not trying to maximize a quality or a cost function that is only based on their own quality of communication. They are willing to improve the overall system performance. But the problem is that they have to deal with uncertainties. So they have feedback that is noisy, and they don't know how the other devices that they are going to cooperate with are going to react, right? Because they also don't know what is the measurement available at the other devices. So the idea here is to use not one neural network, but a series of neural networks that are trained in parallel in a certain manner, in a suitable manner. And the training is going to reflect the fact that at the input informations are noisy, and the fact that the amount of imperfection in the input is different, possibly different at the different devices. Typically, you may have devices that are high-end devices with better measurement capability, and other devices that are low-end devices with more noisy capability. And you want those devices to cooperate with each other in the most robust manner. And this is going to be done through a suitable training of those neural networks. So we've tried this concept for the case of power control. So this is like really a baby scale example of what can be done here. So you see on this picture two transmitters, 1 and 2, and they are trying to serve two radio devices, receiver 1 and receiver 2. And they would like to cooperate in the power control domain. So they want to choose the right amount of power to be able to serve their intended receiver, while at the same time not interfere too much with the other receiver, which is served by the other transmitter. This problem seems simple. However, although it's simple in a centralized setting where you have a centralized decision maker to decide the powers, a centralized decision maker that has access to all the channel gain information. So how the channel strength, how strong are the channels from any transmitter to any receiver. But in a decentralized setting, this problem is extremely challenging because you need to predict what kind of power control policy is going to be used at the other device. And so it turns out that you can use and train the neural networks to solve that problem. And you can obtain some gains. So this is a picture showing the behavior. So I'm not going to comment on all the curves. Just look at the top curve here. This is so. First of all, the x-axis here represents the uncertainties in the measurement at one of the two devices. So typically feedback noise. And the y-axis here represents the throughput of the network. So if both devices know the channels perfectly everywhere, then you can get a certain coordination gain here, which is obtained by this black curve here. And then the blue curve here is what happens if you have a standard policy. Here, the standard policy is a TDMA, so basically only one device is active at the time. So the devices are interfering a lot, so a sensible policy would be that only one device talks at the time. But it turns out that if you properly train the neural nets in the face of those feedback uncertainties, you can have a system where the performance nicely bridges the performance of the optimal centralized system down to the TDMA case, which is unavoidable if the uncertainties are really too high. So if there's no information available at the real devices, there's not much more you can do except taking turns in transmitting in a deterministic manner. So this is the red curve here. Okay, so I want just to say a few words about another topic where we have used machine learning recently. And this is related to UAV-aided wireless networks. So UAVs, unmanned aerial vehicles, or drones. So why are we interested in drones here in wireless networks in my lab? Well, we believe that drones can be useful to provide connectivity where and when it matters, in a way that is highly flexible and that is not possible with fixed deployment of infrastructure. The second reason is that with drones you can improve dramatically the statistics of propagation simply by making a line of sight propagation much more likely compared to communication from a classical base station that is on the ground, and also by providing the content much closer to the end user. So simply cutting the path loss dramatically. But there's an issue that comes very quickly in these type of scenarios, which is where should you put your UAV? If the UAV is acting as a relay, like in this picture here, UAV is acting as a relay between the base station and some ground users, where should you put the UAV? That's again a problem where offline optimization is going to be hard to achieve. You may not have in advance information about the propagation scenario, information about the terrain, and you need to learn all these things on the fly. So we've been using machine learning as a tool to enable autonomous placement of those flying relays so that they can operate exactly at the point that optimizes the capacity of the wireless network for the ground users. So this is the session on use cases. So there's no time to go over the results, but you can do different things. First, there are two kinds of problems when you talk about placement. One is about forming a design of trajectory, so assuming the UAV keeps on flying and kind of visiting the ground user. That's an IoT type scenario where you want to visit sensors that are located on the ground and you want to collect as much data within the battery budget of the UAV. So you can use optimization algorithms to optimize and find those trajectories. And these pictures are examples of trajectories you obtain. These are users on the ground, and this is the start and finishing position of the drone. As you can see, the difference between the right-hand side and the left-hand side is the battery budget available on the UAV. So if you have a large battery budget, there's actually time to fly and visit every one of the users so that you can collect as much data from them within the battery budget. And then on the left-hand side, running the same algorithms, this time with a smaller battery budget, what you can see is that the trajectory gets constrained more and more. And if you have very, very tight battery budget, what you're going to do is that you're going to describe a trajectory that is trying to get as near as possible to most users without actually flying on top of the users. So this is an example of placement problem. Another example of placement problem is if you're looking for a static point where to put the UAV. You really want to find a point that's as much as possible in line of sight to most of the users you want to cover. And that's a very tough problem. The approach that we investigated there relies on maps. And I seen in the titles in the afternoon that Slavomir has a talk about reconstructing maps. I have no idea what you're going to talk about, but I have a feeling that might be related also to the same problem here. So this picture shows a virtual city, and as you can see, there's a drone flying over. And the idea is to be able to learn on the fly the characteristics of propagation, including the characteristics of line of sight versus non-line of sight, to be able to then automatically position the drone. So how to do this? Well, basically, the idea is to reconstruct what is called a radio map. So the radio map is shown here in the middle. This is the true radio map showing the signal strength between the UAV and the user at many possible UAV locations. This is for a single user example. The actual user is located right here. As you can see, this corresponds to this plot here. So the signal strength is highest if the UAV flies on top of the user. However, if you want to relay communication between a base station and the user, the best position to be is not on top of the user. You have to be at a position that offers a trade-off between being not too far away from the base station and not too far away from the user. And that is expressed by this map here. This is the capacity map. And this is really the one you want to reconstruct. And based on this capacity map, you will find that the optimal position of the UAV is actually to be here. This place offers trade-off between being close to the base station, close to the UE, and most importantly, it appears to be in a place that offers near line-of-sight communication. So, and of course, that depends entirely on the topology of the building there. This is something that is very hard to know in advance, and you have to learn on the fly. So we use machine learning for that. And I'm going to give you an example of method we use to kind of predict this map. So initially, you have to realize that we don't have many measurements, so that the UAV is flying and making a few measurements over the city. So we have a few points from that map, and then based on those few points, we try to reconstruct the rest of the map, to extrapolate the rest of the map. Now, there's a different number of approaches to reconstruct radio maps like this. One approach is to use, I would call, a signal processing approach, which is you treat the radio map as an image, and you try to do image processing to reconstruct the image, basically by extrapolation. Now, the method we've tried here is a bit different. I will show you the result in a second. We use an approach called segmented reconstruction, which exploits the underlying physics. So we say that depending on where the UAV is located, then there will be multiple classes of propagation. You will be either in line of sight or non-line of sight, or you can be in strong non-line of sight. So you can have a number of classes like this. And then we use machine learning to do to classify every possible point of the UAV into one of these propagation classes. And only then we actually reconstruct the map. So I'm going to skip the details for that. This is an example of the training we do. So all the crosses represent points for which we have a measurement. This is just arbitrary regular training. And this is an example of reconstruction capability that we have with machine learning here. So as you can see, on the left-hand side, you see the number of training points. So if you have dense training, you can reconstruct nicely the map. If you have sparse training, then you have more errors. But it turns out that it could be okay to have sparse training for the point of view of positioning the UAV. It's actually okay. On the side, I just want to tell you that you can use also machine learning to reconstruct the actual map of the city. And this is actually it's very simple. I mean, based on the idea of shadowing. You make a measurement on a link, and then you have to classify that link as line of sight or non-line of sight. Use machine learning for that. And based on that, you will infer if there's a building on the way or not at a certain height. If you have enough measurements of this kind, you can, in fact, reconstruct the entire schema. And the last thing is that you can actually combine together the 3D CD map reconstruction and the radio map reconstruction, because they're going to feed into each other. So if you have a better CD map, you can actually use it to predict propagation and have a better radio map. And if you have a better radio map reconstruction, you can use it to infer a better 3D CD map. So you can play those games. Now, I want to stop here. I just show a short video that shows an experiment we have done, if you don't mind. So I don't know who has the control over the...
Excuse me?
Yeah, she heard. Yeah, okay. Just to show you an example of putting all of this into practice in my lab for the case of UAV placement. So what you're going to see is that you're going to see a simple scenario in our campus with a user that is moving around. Okay. Well, hopefully the video is safe. Only one.
Thank you, David. So, thank you, David, for the excellent talk. So we have time for 1-2 questions. Yeah, please.
We are with Vodafone. We have a use case for the same concept regarding our product for the cooperation product with Vodafone and Huawei, which is called the crowd cell. I don't know if you are familiar with it or not, but I want to ask you, do you have any studies regarding the power? Hello? Okay. Regarding the power consumption, the power of the equipment, you know that most of these drones is consuming a lot of power during the flying. So our use case was that we use this drone for a relay as you use it, but unfortunately the power was not sufficient to keep it flying and serving the user at the same time for a long time. So even you can see in the video on our YouTube, we used a battery on the ground and wired it to the drone, which limited its movement. So do you have any studies regarding this in your labs? How to improve the I don't know, power consumption? We have some studies right now with Vodafone. We can share it with us offline if you wish. But do you have any vision for the power and how we can save the power of the drone to do the two function by flying and keep the user connected? Thank you.
Good question. Yeah, this is one of the limiting factors. We think that just flying over consumes about 90% of the power, and 10% goes for communication power. And our drone can fly about half an hour, which is okay for experiments, but not enough for every product. But we have pushing some system level concepts for dealing with this problem, and we can modify the algorithms so that the drone can position itself to what we call landing posts. So these are places that can be easily found in the city or in the nature, where the drone can actually rest without flying and continue transmission before moving to the next position. And you can save really a lot of the consumed power by doing this. If you want, I can send you the paper with studies.
Please. Okay, so now just let's move to the second speaker because of time. And thank you again. So the second speaker is Ahmed Al-Assad from Volkswagen in Germany. And so Ahmed is going to talk about 5G for automated driving 2.0.
Thank you, Salvomir. Thank you very much. Ladies and gentlemen, it's a pleasure for me today to be here to talk with you about our vision or our requirement from automotive point of view on 5G communication technology. I'm actually representing my colleague, Flattening. He is working on the digitalization, in the group digitalization. I'm working on in the group research. So 5G for automated driving 2.0. Maybe it is good to know first about the history. Now the state of technology, what we have for automated driving is a generation 1.0. With the current technology, we are able to use the onboard sensors and the in-vehicle maps, and in order to develop functions and applications for automated driving. It is completely functional without any connectivity, and the systems are self-sustained. But we want to extend our systems, and therefore we are looking for the development towards automated driving 2.0. We want to extend the onboard sensors by 5G connectivity in order to increase the ride efficiency and also to increase the customer comfort. Adding new sensors, especially 5G communication, will enable the development of new connected automated services or applications, and enhance or in turn we will have also a new business model. We have to agree with the telecom industry in order to establish the realization of this new applications. So what are the requirements, and to which sections or which areas address this requirement? We have listed here 4 technologies or 4 topics. One topic is the narrowband IoT. The second topic is the coverage topic, network slicing, and predictive quality of service. So for narrowband IoT, we have 2 main requirements. The first requirement is we need deep penetration as an enabler for automated parking, and the second requirement is we need the long battery lifetime despite quick wake-up times. The open questions for penetration is let's think about parking garage. The main question is what or to which level in underground parking garages we will be able to send or to send and receive signals with narrowband IoT. As it's a question of penetration. We are discussing now about 2 plus 20 dB gain in comparison to regular LTE, but it needs to be validated, and that is a point what we need to discuss with telecom operator, and also to discuss if there is any further improvement required, for example, with hard repetition or other methods, and the communication stack. So, the coverage topic is another topic. We need good concept for provider interoperability. We need also side link functionality. When we are out of coverage. The side link communication is the PC5 link is one of the main links where we can support also 11B on the 5G or the 5.1 gigahertz band, but it should be operated on another band, not on the 5G.9 from Volkswagen point of view. The side link functionality is a topic, and a further topic we have to talk about the area coverage, and especially what do we need really in this area coverage. Do we need control plane or user plane? That is a topic which we have where we need to discuss or when to talk together with automotive industry and telecom industry. Network slicing is one of the most valuable concepts in 5G communication. It is also wide discussed in many papers, in many white papers by telecom industry. Even Volkswagen has also published one paper about the network slicing with Deutsche Telekom, with Huawei, and China Mobile. The main challenge for network slicing from automotive point of view, that the use cases in automotive are very dynamic. That means the network slicing need an interface to quickly adapt the communication requirements. That means the UE should be able to set each KPI separately. The reaction time need to be investigated, but need to be foreseeable for the car manufacturer. We think about 2 interfaces. One interface between the application and the UE, and the other interface is between the UE and the network. That is the basic for the next point. The problem is how we see network slicing is we would like to have our slice everywhere when we want, when we need it. The current state of technology is we have a slice, but it might not be always available at each location or at each time where we need it. Therefore, we thought that predictive quality of service can be a solution for to optimize our application. And the idea behind that is to have more to replace the quality of service guaranteed by predictive quality of service KPI. The major improvement what we see from car manufacturer point of view, we will be able to adapt our the settings of our application depending on what has been predicted on KPI, for example, for data rate capacity or end-to-end latency. The improvement what we see from a mobile network operating for mobile radio operator is that quality of service requirements do not need to be all the time continuously provided to the car. It is enough to say, okay, in the next time horizon, the quality of service KPI will be available in a certain lower bound, for example. And the point is that from automotive point of view, we will be able also to support this prediction process by providing some help information like the expected route of the car, the time horizon, what our application requests, and also some measurement from the UE, like the channel estimation, the channel input systems. So for that purpose, we propose concept which called ACOSA. It is abbreviation for Agile Quality of Service Adaptation. It is a closed loop to interact to model the interaction between the application and the network. If you see, we start if you take a look here on the figure, we start here on left top. The first step, the application has to set its initial requirements in terms of data rate capacity or end-to-end latency, and also the predicted path and the time horizon for needed from application point of view for the prediction, and send over a predefined or specified interface between the application, between the car and the network, the QoS requirements. The network receives this information via the specified interface and assess the feasibility to provide this quality of service requirements, depending, for example, on machine learning algorithm or other algorithm. It depends. It is up to the network provider or up to the network telecom industry how to assess and how to investigate the feasibility to provide quality of service, and how to predict them and to provide them to the application. As a response, the network answers with the predict quality of service. It is via the specified interface. And this predict quality of service contains which KPIs can be available or are available for the application for the search for the expected route of the vehicle, and for the required time horizon of prediction. Once the application receives this information, it is able to adapt its setting, and in order to optimize its performance, and then can submit the next QoS requirement to the network again. It is a continuous process, and that is the way the general model how we see the quality of service adaptation and the interaction between the application and the network. As an example, it's always good if we talk about concrete use cases, high-density platooning. The benefit of high-density platooning is if we have short distances or as close as possible, or gaps as close as possible between the tracks, it is feasible to increase the road efficiency and simultaneously also to increase the fuel saving. Problem is if this information is not, or this distance is not available, or the prediction is not available, then we have always to drive with the maximum margin, which considers the uncertainties and the communication between the tracks, and in order to keep the safety, because safety is priority, but we will have a lack on the efficiency. But with quality of service adaptation with ACUSA, we can adjust the distance according to the current road conditions, the vehicle types and the models, that means the control capabilities of the vehicle, the load of the vehicles and their ordering, and now two different and now two additional criteria are the forecasted link latency between the tracks and also the data rate distribution between the tracks for the data transmission. And based on that, the controllers in the platoon will be able to optimize simultaneously or to keep the safety, the stability of the platoon, and simultaneously also optimize the setting of the distance and the inter-vehicle distance, and in turn also the fuel saving. So, the summary: narrowband IoT, it's evolved, deep penetration and data rate is required. Coverage topic, area coverage, for example, for control plane can be discussed. When we talk about network slicing, from automotive point of view, we have to consider the dynamic aspect of our use cases and their continued changing requirements for quality of service. Therefore, we talk here about dynamic network slicing. And predict quality of service, we think, or we are convinced that predict quality of service is the enabler for 5G, for automotive use cases, for 5G communication in the future. Thank you very much. Questions or comments?
Okay, thanks, Ivan, for the nice talk. Now we have time for questions.
Good morning, thank you. I have a question on behalf of Ashwini Satnur, on the node participants, who would like to know which types of vehicles would be targeted for provision and predictive channeling and routing.
Sorry, I couldn't understand your question.
Which are the types of vehicles that would be targeted for provision of predictive channeling and routing?
Yeah, I mean, the vehicles, when we talk about vehicles, they would be the passenger vehicle and also the heavy vehicles. All vehicles can need pretty quality of service. It depends on the application. I can give you two different examples. For example, when you drive from A to B on the highway, and you have some tele or video conferencing application running, for example, if you have a predicted quality of service on the way from A to B, it is possible to adapt the data rate and maybe the coding scheme of the content according to the predicted quality of service in terms of data rate capacity. And that is for passenger car can be very good use case. For platooning or underground mining, it is also another totally different use case where we have to predict the quality of service in order to adapt the gap between the gap between the tracks to optimize the fuel saving and optimize and simultaneously to keep the safety in the tracks. That means all thinkable vehicles can be a target for predictive quality of service technology.
Okay, thank you very much for the clarification. I have two more questions, if I can keep the floor. One from Martin Adolf, who says good talk and would like to know where can he find more information about the AQOSA. Is it defined somewhere or described in a paper?
Okay, where we can find about AQOSA, you mean? Okay, it is not described yet, but it will be a topic on the 5GA next week. That means if you are in Munich, and that is the first time. I mean, we wrote a white paper with some telecom partners, and we submitted to the 5GA, and it will be a topic next week. If you are involved there, that you will be also involved in the discussions.
Thank you. One final question from Vincent Donjon, Interpol, who would like to know, do you anticipate logging ACOSA so it can be investigated after an incident?
Again, please. I didn't understand the question. Yeah, it's difficult.
Do you anticipate logging ACOSA so it can be investigated after an incident? This is from Vincent Donjon, Interpol.
Yes. Okay, I mean that you talk about trials and how to validate the ACOSA. Yes.
I can only repeat the question if you like.
Yeah. Okay. Fine.
Do you anticipate logging ACOSA so it can be investigated after an incident?
Okay, I mean that how we can investigate ACOSA, we have then to specify applications and to dig up some trials and to I mean, I'm sorry, but the question is not clear.
Okay, another comment to says ACOSA will change the vehicle behavior, so we need to keep traces of the decisions from the same person. That's all they want.
We have
to keep the trace of decision.
Yes. We have. I mean, we have to keep the trace of decision. I mean, the decision should be taken always by the car, but we use the information from the network to optimize our application in terms of route, in terms of adaptation of the controller behavior. That means the decision is always taken in the vehicle, and we use the information as help, but we don't allow to control our vehicles by the network.
The way I understand the question is, if there's an accident and you want to find out whose fault is it, are you logging the information of this AQSA?
I mean, we are not so far now. I mean, we are not so far to consider some special cases of accident or special cases. We are now thinking at the beginning about how we can allow the interaction between the car and the network, we are talking about the interfaces between the network and the applications. But special cases are not considered yet. It is in our agenda, but it will be in future topics.
So maybe last question from my side. I think that this would be a good topic for this focus group, because 5GAA is just a closed community. Not everybody can attend this meeting. But do you think that just a QS prediction, this is a good topic for the focus group, machine learning, future works, including 5G?
Yes, I mean from as a topic it matches very well. We have, but it is from technical point of view, I think it fits very well. But we have then to take an internal decision how to proceed with that. Yeah, I mean, and from strategic point of view. But
the question is, it's not implemented, so you need cooperation or interaction with network operators, right? And so just you cannot do it by yourself.
That's right. I mean, we are also in contact at the moment with some telecom partners, and we also plan with them to validate the ACOSA concept via trials in Germany. But I may not talk more about that. Sure, this workshop and this focus group is matched very well with this topic from our point of view. But I think we need first to clarify internally at BW how to proceed strategically, and how we can contribute to this focus group, and also to learn with you how we can implement and validate ACOSA maybe for different use cases, not only for platooning. We are also interested to investigate the impact of ACOSA to the quality of service for other use cases.
Thank you. Thank you very much. To continue with the microphone. You have to push this. Sorry. So we have to hear, just when we speak, we have to push the button. When we don't speak, we have to push again. So it's not so easy. Okay, so let's proceed with the third talk. Yeah, thank you. Use cases and requirements of network intelligence given by Young Hong. I hope the pronunciation is okay. So the floor is yours. The switch. Okay.
Okay, thank you. Good morning, everyone. My name is Yong-Gun Hong. I'm working for ETRI in South Korea. So it is my pleasure to have this time and with you. So in this talk, I present the use case and requirements of the network intelligence. This is the agenda. Yeah. When we consider the 5G network or IoT, IoE network, we can find some differences, the originality of the internet, because the internet was made a long time ago, but nowadays, the 5G or IoT internet, there are many new requirements. For example, there are lots of the connected devices, and the traffic is mobile oriented, and there are many high level big volume of the traffic volume, and there are many requirements of the conference devices. Also, we need real-time and reliable communication. So to support these requirements, there are many ways, but we believe that machine learning or AI is one of the ways to support these requirements. This is in S3, my research institute. We are under this project, that is the Knowledge Conversion Soup Brain project. So in this project, we collect and monitor data, and these data are refined, and these data are transferred to AI platform. And in AI platform, we do inference and optimization, and the result is transferred to real services. For example, energy consumption, brand safety, healthcare, traffic optimization. So in this big project, I'm involved in the intelligent IoE network. So in this project, I have two questions. So to provide the full services, what is the role of the network? We need to new AI for network, or do we need to network to utilize AI? So it is my concern, and it is my ongoing consideration how to utilize the intelligent IO network. Okay, so as I said, that nowadays the network paradigm is shifting. So, originally, the network is network itself. So the basic role of the network is to deliver, transfer traffic packets without any operation. But nowadays, we are talking about network intelligence and intelligent network. To do this, we believe that there are something to do in the network itself. For example, router, gateway, access point, base station, something blah blah. And if then we believe that the raw data can be converted to information, to do this, we need to prove processing data and adding extra value, and we need some data analytics. If then this information can be converted to knowledge, and finally, our main goal is to make some wisdom in the network itself. I know that it is a kind of the novel, but if we provide the 5G or IoE services, I believe that network should or could do some kind of the work. So if we think about the use case of network intelligence, there are many use cases. For example, the DOS attack. If we compare the URL or the data path between general cases or abnormal cases, then we can get the DDoS attack, and we can do some more efficient for the network management using AI, ML, or if you provide a self-organizing network. So autonomous driving is one kind of the self-optimization network, and we also do some traffic classification. Okay, so during our project, we found some typical use cases and typical requirements. So in this time, I would like to share our experience with you. So the first use case is to information-centric intelligence layer. So this is the challenge of 5G. If you look at the white paper or other documents, you can find that information-centric approach is needed in 5G, and mobility management and enabling AI is required in 5G. So we would like to design of information-centric intelligence edge. So in this, we want to do some data cache storage, via analysis of user service requests, and we also want to make some system mobility management via analysis of user services type. Yeah, so we compare to three ways. That is, first one is the cloud-based data acquisition. The next one is to basic ICM-based data acquisition. And the final is the intelligent data, edge-based data acquisition. So the final one, to do the final one, we design and made the intelligent data cache storage. So in this system, we made some on-demand cache and pre-fetching cache and intelligent cache. So it is the rough result. So you can find that the time to acquire data or ratio of the packet loss is the final intelligent edge is more better. Also, if we use the information-centric intelligent edge, we can provide more efficient mobility management enabled with AI. The second use case is the ML-based traffic classifier. The purpose of this traffic classifier is to continually collect traffic data and then build traffic classifier model based on collected data and classify and predictably update the generated model. So in this system, the key function of the traffic classifier is for the first one is the machine learning model for traffic classifier, and second is traffic data miner, and online data runner or classifier, and finally the web-based monitoring tool. So we to classify the data traffic, we use two models. One is to CNN, and the other is RNN. The CNN is used to per packet running, and the RNN is used to flow-based traffic classification. So in our system, we check the 5 tuple and take it in count, and we decide which one is better to use, the CNN and RNN. So we can make some results of that. We can not high score of the accuracy, but we can get some the relevant and the average of the accuracy of score to classify traffic. So it is the system computation. So this is the level packet collector to sum the level packet information to the server. So in this server, it builds deep learner, backtester, and web MySQL server. And this result is transferred to the virus AP based Linux. For example, using TensorFlow serving mechanism. And in this virus AP based Linux, it do model serving, packet snipping, and classifying and logging. And the final use case is that the smart construction. So the purpose of the smart construction is that implementation of monitoring of service of construction. And in this service of construction, the characteristic is scalable media data transfer based on alarm. So the purpose of the POC-based smart construction services, we collect construction data, one noise, one vibration, and 5 kinds of gas, and the 4 types of video data. And we want to transfer this data to central cloud. So in the Korea, in the Yongin Sea, in the year of the universe construction, the real test bed was set up. As I said, that this kind of the information was gathered and transferred to the cloud. So if some accident was happened or some argument was happened, we can search this transfer data in the database. But you know that the noise and vibration and gas, the volume is not a problem. But we use the 4 type of the video, and this video is a little big volume. So if we transfer this volume to the cloud, network traffic is a kind of the problem. So our goal is to reduce this kind of volume to the small size volume. To do this, we predict the 4 kinds of the gas, vibration, and color information. And we, in the normal cases, we transfer to the data to SD or HD scale. But in the some accident case, then we try to provide high quality, more high quality to the cloud system. To do this, we did some exact accuracy system to predict these cases. And if we are doing some kind of the use cases, we found some of the relevant requirements. The first one is to data processing support and mobility support and real-time communication support and reliable communication support. And also scalability, constraint environment where easy deployment forces are also needed. And if we look at other SDO documents, we can also find some requirement. That is we need to look at small scope of assumption that behavioral network, and we need data set and the problem with a talented tool, and we need to start using specific fields such as SM-based architecture, and we also need to identify new scenario, and we need to have a well-documented format, and we need to approach with a classical ML-based technique. Okay, it is my conclusion. We talk about the network machine learning. We believe that network machine learning or network intelligence is required to support IoT and 5 services. But we found that there are many problems and difficulties to provide network machine learning. One is we don't have so much enough data set and the model, because many data sets and the models come from image or voice or text recognition. If we convert to the network, it is very difficult. So in some cases, we made a new algorithm model to deploy in the network area. And the other difficulty is to the network behavior complexity. If we recognize or if we classify, it's kind of simple. But if we predict or if we imagine the full network operation, it is not easy. It's kind of the guard area. So if we need to make narrow focus of the network machine learning, it is more important. And the final difficulties is that there are many diverse and various understanding of network machine learning. I remember that if we make some standardization activity of IoT in ITF or other sphere, there are many debates. What is internet and what is thing? It is the same situation in the network machine learning. If we look at or talk about network machine learning, there are many approaches and there are many experts. The network expert and AI expert and the other service domain experts. I know that we need to integrate, we need to collaboration between them, but there are many view and many understanding of the network machine learning. So even though there are many difficulties, I believe that it is the time to start the research and the standardization of network machine learning in this area. So I hope in this workshop and in this focus group, I have get some of the answer of this question. Thank you.
Thank you for the inspiring talk. So now we have some time for questions. Okay, so from the remote participant there.
There are some questions. I have a question from Ashwini Satnor, and it's would the intelligence network also include the communication in the aerospace subject areas, that is including aerospace satellite communication with the help of telecommunication links via mobile communication? It's a long question.
So I'm not expert of the aerospace area, but I think that yes, it's possible. Yeah, but actually in our team, in our lab, we do not have some experts of that kind of area. But if we utilize the network machine learning or network intelligence, then we can deploy that technology to the aerospace area also.
Thank you. And the other one is from Bhavna Ambudkar. Does this relate to Internet or things also?
Yes, so in my talk, our project is related to IoT services. So our talk is many parts are related to the IoT, but we talk about the network machine learning. There are some different not related to IoT. It is related to the 5G, or it is related to the general network area. So my answer is that in my talk, many parts are related to the IoT, but if we think about the network machine learning, the answer is then no.
And the last one is from the same person. It's, are we going to work on new protocols or modify the existing robust ones?
It's a good question and important question. Yes, I believe in the time goes by, but nowadays previously we need some of the common understanding of what is the network intelligence and network machine learning. So we must investigate the use cases and requirements and some relevant architecture, and then we possibly invent a new protocol to satisfy this requirement.
Okay. Yeah. I have a question here. I want your vision about the fog or maybe the edge of the cloud. You can say. Do you only want to collect the data from this fog layer and send it to the cloud to have the machine learning work there, or you want to turn or take the intelligent into the edge. So this is my question. I want your vision, because I have some thoughts about why we don't drag the intelligence from the cloud to the edge.
Yes, it's also a good question. Yes, if we utilize the machine learning or AI, we need the server or high efficient machine. So to do this, it is the best way is to deploy in the cloud and gateway in the cloud. But as I said that if we think about the IoT and the 5G services, requirement is that real time and the reliability. So yes, we can calculate and we can analyze in the cloud area, but to deliver to the service to the end user site, it takes a long time. So the best way is to real devices and real user site is the best way. So I believe that cloud and edge may have their own role, but if we integrated or cooperated edge and cloud, then the full efficiency is more increasing.
So thank you. Maybe the final comment from me. I think that in one of your slides you said that you need highly reliable communication infrastructure. So I think that the topic could be for the focus group to talk about whether we have to make the ML algorithm robust in the sense that they can cope with uncertainties we have in the wireless communication. So because just maybe to require highly reliable communication infrastructure may be very costly. So I know from Industry 4.0 that many vendors and operators are not able to or are not willing to accept high costs. Okay, so thank you again. And now have a final talk in this session. It's AI stands for Artificial Intelligence, right? Applications in Telecommunication Network, given by Shang. I hope it's okay. From AIIA.
Hello, thank you, Chairman. Hello, everyone. I'm Cheng Chang from the ICT, and I'm also chair a telecom task force in the Artificial Intelligence Industry Alliance of China. My presentation will give an overview of the applications of machine learning in telecom network.
Doesn't work. Yeah. What was it? Yeah.
Free.
Yeah, no.
We have to wait, but the wireless is not the problem. Sorry for this, yeah.
Okay. Artificial intelligence is, have a long history from more than 6 years. But recent years, machine learning as a subsection of the artificial intelligence shows great progress. For example, in the medical certification area, there are ImagineNet competition hold for 7 years. In the first one, the success rate is 72% in 2010, but in last year, the success rate up to 97%, and machines also dominate almost all table games. 10 years ago, the chess has been defeated by the Deep Blue, and last year, and the human cannot win Go games. AlphaGo defeat China and Korea top players. In the early of the last year, AI also defeat top poker players. Also, machine learning make big progress in many other areas like robot, autopilot, natural language processing, etc. And machine learning already have been used in our everyday life. For example, in mobile internet, finance, medicine, and education. For example, this is a screen capture from our smartphone. There are many apps use machine learning technologies. For example, for speech recognition, classify photos, sort the news feed to us, translation, record schedule, and precision advertising. Why telecom network needs machine learning? The first one is network operation and management is more complex along with network evolution. Software plays a key role in SDNFA. Diagnostic across multi-layer and multi-domain is a difficult task for a current person. And a lot of information that hide in logs, alarms are omitted. We have no time and no resource to analyze it. And automation is needed to improve the efficiency and reduce the OPEX of the network. The second one is a new service and new applications require for new network capability. The programmability and flexibility and the high level of mission of 5G operations create new service paradigms, which might be even beyond our imagination. For example, for applications of the Internet of Things, tech internet, advanced robotics, and immersive communications, all these are new things in network. These new applications create challenges of network scale and traffic volume. Network needs to manage complicated resource and dynamic traffic intelligently. The last one is machine learning provides new service opportunities for telecom network. Many applications, for example, in industry or in business, need machine learning computation platforms as service. So telecom network can provide lots of service to support these applications. Then I will give some example of machine learning scenario used in telecom network. First one, machine learning based language or speech processing have been used for seeing lots of labor code. And machine learning also makes the UI, the device UI work naturally. For the machine learning used for subscriber service, one is chatbot can reply customers' questions automatically. Use machine learning used on various service channels. This chatbot can be used on website, instant message, and SMS to serve the customer. China Mobile's chatbot named Eva online in 2016 have served more than 50 million replies per month and save 100 million RMB cost per year. And also China Telecom have service robots that can listen and answer questions from customer by voice. This robot have been shown in Beijing store. Another use is use speech interface for home device. Some IPTV set-top box or OTT box use speech UI can control all search program by the voice. Another use in network is used as operation maintenance and optimization. Machine learning has potential for a broad range of applications that can improve network design, operation, and optimization. Here we give some examples. For example, use in fault management. Use machine learning algorithm, we can find connections between different alarms and extract knowledge from network logs. Rapidly locate the root alarm. Troubleshooting by alarm log statistic collections by multiple source analysis. The second example is we can use machine learning for fault prediction. There are lots of components like laser used in the network device. Machine learning can analyze optical monitor parameters. For example, ORM function in the ONU or ORT and collect the parameter to predict the failure of laser. And analyze data center server IO status values to predict failure of hard disk, or analyze DSL line errors and SNR to predict the DSL service quality. By help of fault prediction, the maintenance could be scheduled very easily. The second example is using machine learning to help the data center save power consumption. The machine learning algorithm learning the server's load, power consumption, temperature, lots of parameters, set up the model, and to predict the server's load by time, trigger migration, task migration, and trigger the server to low power mode to save power consumption. China Telecom has applied this method, saving $80 per server per year. Also, machine learning is a complex stack. It's an opportunity for open service. A large number of machine learning applications require different kinds of computation platforms to serve them at different levels. At the lowest level, the server, virtual or physical server optimized for machine learning could be optimized. For example, CPU, memory, I/O can be optimized. And furthermore, heterogeneous computing with CPU accelerated by the GPU or FPGA or ASIC could be deployed in the data center to provide the service. In the middle layer, operator could provide machine learning computation framework. For example, there are many of open source machine learning frameworks like TensorFlow, Caffe, MaxNet, Torch, and so on. To build this software framework is complex and cost high for the user, for the client. So service provider could provide this framework service. In the high level, some common machine learning video or image of each service could be provided. For example, to recognize license plate, human or traffic or record, traffic monitor, face identification, or natural language processing. And also, machine learning can be applied to networking. Network itself, but so far are more or less related to prediction, classification, and decision-making network area. For example, machine learning can be used for information cognition. Information cognition with high efficiency is critical to capture network characteristics and monitor network performance. Machine learning can help evaluate network reliability or the probability of the certain network state. Second, machine learning can do traffic prediction and classification to estimate the traffic values. It's beneficial to congestion control, resource allocation, network routing. Many studies focus on the reducing the measurement cost by using indirect metrics, because the direct metric to the high-speed network is very difficult and cost high. Machine learning approach based on statistical feature also have been extensively studied in recent years, especially in network security domain to do traffic or packet classification. Next one is to do resource management and network adaptation. For example, address traffic scheduling, routing, and TCP congestion control. These issues can be formulated as a decision-making problem. A deep reinforcement learning achieves great results in many problems. Last one is using network performance prediction and configuration extrapolation. Example applications are video QoE prediction, CDN location selection, best wireless channel selection, and performance extrapolation under different configurations. Also, machine learning is expected to play an important role in future network model. A-Matrix et al. Published a paper defined knowledge-defined networking in 2016. Knowledge-defined networking define a new paradigm that accommodates and employs SDN, network analytics, and AI. This model adds a new knowledge plan to the traditional three plan of the SDN paradigm. This paper also gives some operate mode like closed loop and open loop. That make for closed loop, the knowledge plan will make decisions automatically on behalf of the network operator. And for the open loop, the network operator is still in charge of the making of decisions. So here we, based on this demonstration of the application, but there are still some factors prevent the application of machine learning network. The first one is non-deterministic. Typically, network operators operate with deterministic protocols that are well understood, but the output from the machine learning model usually lack of interpretability to human. The second one is data issues. All machine learning is data dependent, and the performance of machine learning algorithm is affected largely by the nature, volume, quality, and representation of the data. So high quality data is, but high quality data is expensive in time and money. Second one is validation. Machine learning algorithm needs to be selected carefully for different problems, and the training model should be ready to avoid overfitting. Diagnostic and tuning model is not easy. And then the performance of the model of the algorithm may be not fit to the delay sensitive service. And the error sensitivity, especially in network automation, some high cost is sensitive high cost brought by the learning errors. So the summary is dealing with complex problem is one of the most important advantage of machine learning. And machine learning also has shown big potential to many aspects of network. Research, industry, and standard developing organizations like ITOT have a lot of work to do making machine learning play a valuable role in telecom network. Thank you.
Thank you. So we have some time for questions. So maybe one question from my side. You said that all ML algorithms are data-driven. So at least in our community, there's some activities, to go towards hybrid-driven algorithms. They are data-driven, but they are also model-driven. So which includes expertise knowledge, which is extremely important for the algorithms to work in and to provide the desired reliability. So I think that this is an excellent topic also for the focus group. The question is how to incorporate the expert knowledge into the algorithm in a systematic way, and to come up with hybrid-driven algorithms that are both based on data and model.
Yeah, it's a good question. Traditional machine learning like supervised algorithm is sensitive to the data quality, and also but high quality data is very difficult to get. There are some research, for example, recently, to semi-supervised machine learning algorithm to mitigate this problem. And also, I think to cooperate with the expertise system is very valuable for this area. And I agree with that.
Thank you. And then I would like to conclude this session. We are on time. Oh, I am a hero. And now, so we have, like 20 minutes coffee break, and we are very happy about this. Thank you again for the excellent talks.
Meron. And okay, let's start. We're still missing one speaker, but I'm sure he'll be here in a minute. My name is Kim Wahner. I'm with Fraunhofer HHI, and I will moderate this session. And this session is about challenges and opportunities for our topic. I'm curious to hear what our speakers will have to say about that. And our first speaker is Jakob Hoydes. He's with Nokia Bell Labs. Floor is yours.
Yeah, good morning, everyone. Good morning, everybody. It's a great pleasure to be here. It's my first time at ITU and also in Geneva. I'm very happy to be here. So as was said, I'm a member of technical staff at Bell Labs of Nokia, based in Paris. I'm actually an expert on the physical layer. I've worked for many years on massive MIMO, and around 3 years ago, I made the decision to switch research topics, and I moved to the applications of machine learning, in particular deep learning and deep reinforcement learning for signal processing applications in communication. So I've gathered quite a lot of experience in the last 3 years, but I think since this is an inaugural meeting of this focus group, I just would like to share some thoughts on the general promise of machine learning for communication. So it's really a high-level presentation, but I think there are a couple of very important questions in there that all of us should ask ourselves. I just start with a citation from a paper by two MIT researchers who essentially say that machine learning is the most important general purpose technology of our era, similar to the steam engine, electricity, and the internal combustion engine. And when you see such statements, I think you all agree with me that you say, oh, I would like to apply this technology to my field, to my industry. And so I think the whole problem we are now facing is how can we actually leverage machine learning for 5G, or maybe what comes beyond. There's one way how it doesn't work. And this is by hiring machine learning experts. And there's a reason for this. There's a quite nice analogy between Maslow's hierarchy of needs of humans and the machine learning application. That the human needs, to sleep, we need to eat, we need to satisfy our physiological needs. A machine learning algorithm requires, first of all, data. And so that you can make many of these comparisons at the same level, but the key message is that before you can even apply the most basic machine learning algorithm, you need to do many things. You need to collect data, you need to move and store them somewhere, you need to explore or transform this data, you need to remove anomalies, you need to clean the data. Often, and this is the most expensive part, you need to aggregate data, label them, sometimes even by humans. And all this needs to be done before you can even think about trying to use machine learning. And so, in essence, 80 to 90% of the work that needs to be done is not really related to machine learning. It's like very unglamorous, dirty plumbing, which simply needs to be done before we can actually proceed. And so I think our industry is currently in a situation similar to HD television when there was no HD content available. So you actually bought a TV with the sticker HD ready on it, but you actually had no idea what does HD actually mean. There were no HD movies. And I think right now in telecommunications, the practical gains we can expect from machine learning and AI are quite unclear. But still all of us would like to label our products being AI ready. But if you speak, I think there are many operators here. I had the chance to speak with a couple of them. It turns out that even gathering very simple data today, network-wide, is very difficult. I was really surprised to do this. So having high quality, clean data that has been collected in time instances across multiple cells is extremely difficult. And if you now take into account that there will be a tremendous complexity increase from 4G to 5G, we all agree that in some sense we need to rethink and build our networks with AI application in mind, although we don't really know what we're going to do with the data we can extract. Okay. Now I have another reason why I think that data is so important. Here's a statement from someone called Enrico Pazzi, works on AI at Tesla, and he said that for many real-world problems, it's actually significantly easier to collect data than to explicitly write the program. And now if you take this seriously, then you can make the analogy that the source code of our algorithm is going to be replaced by data. A compiler that compiles source code is replaced by a deep learning algorithm and training of the deep learning algorithm. And the executable, so the piece of software that you would actually like to run, is actually replaced by a trained deep learning model or another machine learning model. And this could be how we write software in the future. Now I'm just saying this because if you have bad source codes today, our algorithms simply don't work. And I think similarly, if you base products on data and your data is not good, then also your machine learning model. It's all about data. And now there's one caveat on the last slide. It says that for many real-world problems, actually this holds true. It's more difficult to write an algorithm and collect the data. Now the question is communication actually a real-world problem? And it depends on, I think, on the layer where we're looking at. Because where machine learning, in particular deep learning, shines is in areas where we don't have a model. For example, in computer vision, writing an algorithm that detects a shoe in an image by hand is an almost impossible task, but it's trivial to do this today through deep learning. But if you now go to the communications domain, this is a man-made system where we have extremely good channel models and system models. And for example, everything what's happening on the physical layer is extremely well modeled by our knowledge today, and for this reason we have close to optimal algorithms in many scenarios. So I think in many cases machine learning doesn't have the huge potential to lead to any significant improvement. And I think the only areas where we can expect to make significant performance gains is in complex scenarios that are hard to model or to optimize for. Now I just have a, when I speak in our company with people, so we have several hundred projects on AI going on, and often you can eliminate if this is a good use case or not by asking a few simple questions. And here's a kind of set of questions you should ask before you think about even applying machine learning to your task. This is also something taken from another paper from the same MIT professors. And essentially, here's a list of 4 things you need to make a machine learning problem suitable. First of all, does it require a mapping from well-defined inputs to well-defined outputs? The first criteria you should essentially have. If you can't provide clear feedback and you don't have any clearly definable goals and metrics you can explain mathematically, it also is not a good fit. As I said, we need large, high-quality data sets that you can either record or even generate synthetically. In many cases, in communications, you can make simulations to avoid gathering data. And another point, and I think this has been also alluded to, is that can we accept to make errors and live with approximate solutions rather than having something very precise. And in cases where it really is not a good fit is when you need a lot of detailed explanations of figuring out how the decision has been made. If you need long chains of logic, is also something machine learning tools today cannot provide. If you have very rapidly changing conditions, or if your data you actually need to train your model changes very fast, essentially the stochastic properties of the data change that you don't even have time to train a machine learning model on it, and it's also not a good fit. And in some cases, you even need to be able to actually interact with the physical world in some sense. In this case, if you don't have a purely digital system, it also doesn't work. Now where we currently see high potential areas, they're only on the slide. I just want, before I go through them, I want to say that there's explicitly nothing about the RAN on it, because I think this is a very optimizing anything on the RAN, so really a high challenging goal, and currently this is not where we see the biggest potential. So where I see best fit is actually more on the analytical side. For example, predicting customer experience, provide automated interactive dashboards, detect anomalies, etc., traffic classification. These are all things where you essentially, you don't take a decision and you don't interact with your system. It's rather about detecting things, providing insight about what's going on. But really the optimization part, where you would like to act on your system, optimize metrics, and react and learn from interacting with the system, this I don't think is not something we can do today. I've seen there's a talk later about deep reinforcement learning. And I think the biggest problem we have there is that in order to learn through reinforcement learning, you need to have an environment in which you can act. And I don't think that anyone would be willing to let someone play with an existing system just to learn. So this whole question of whether we have actually an environment, a standardized environment that we could use, from which you could learn, is I think a very critical challenge and question. What I expect from this focus group is essentially what we're already doing today, discover and discuss use cases that I'm not aware of. And I would like to discuss about mutual pain points. I think high quality data is something I'm not the first one to mention. I would also like to develop an understanding about standardization needs. And since there are a lot of also academic people here today, I think it's important to identify research gaps. In particular, what are the areas which are not currently covered by the machine learning academic research, which is mainly focusing on computer vision, natural language processing, and so on. I think there's really a niche on what does machine learn, what needs to be developed to apply machine learning techniques to telecommunications related problems. And that's already from my side. Thank you.
Well, thank you very much for this interesting talk. Are there any questions in the audience? Yes, please.
Yeah, just thanks a lot. I appreciate this talk. So first of all, I would like to say that the world is not white-black, right? So I mentioned that that maybe today all the algorithms are completely based on data, yeah. But we could have this hybrid-driven stuff. But what I want to say is, you said that today we have extremely good models, okay? So, but if this is a relative, everything in life is relative. And to say good models, you have to say for what? If you go to applications like Industry 4.0, where you have, for example, requirements 10 to the power of -9 or -12, and the latency constraint of 1 millisecond, the models we have are not good enough. And then if you go to higher frequencies like 28 gigahertz, 60 gigahertz, and they are just now, people in Germany are strongly interested in using these frequencies, for example, in the context of Industry 4.0, then even you don't have time to estimate the charge. So then, the question is really, if we have, very good channel models and time to estimate them, and then, whether, machine learning could close this gap, use the machine learning for fine-tuning. This is just what my question is.
I don't know what the question precisely is, but I agree with many of the things you've said. The thing is, the reasons why what I've said is that so far I have not seen a single application in communications where machine learning has enabled something we couldn't do before. And this is normally this just makes me a bit skeptical. So in many other domains, in computer vision, you see things where you say, wow, this is not something we could have done otherwise. In communications, I haven't seen this. And I haven't seen any really breakthrough application so far. I mean, it's new, it's early days, but I think what we would really need is a number of high potential success stories to actually convince people that this is really making a difference, and we can do new things we couldn't do otherwise.
Yes, please.
So I want to ask something about, you said that we shouldn't look to the machine learning right now because we cannot. The first question that you said, or the fourth question that you are illustrated, that we cannot know how this decision have been taken by the machine, because this is normal for the machine learning, it's a black box. But I think that, for example, for the RAM or for the access network and the error interface, right now you cannot find an expert human that can predict the behavior of the waves among the error. So most of this prediction, I don't think we have sometimes right now some undefined behavior for the waves. For example, we have undefined group codes, for example. We have some undefined wave behavior. Maybe it's like a constructive interference, destructive interference. And I think that most the machine learning algorithms maybe cover this unknown prediction, and the machine will know it and will define it as a variable. It cannot tell us about what is this, but it will cover it. So I think that, for example, the artificial intelligence and the rainforest, for the SONO example, for the physical authorization network, it will be good to enrich the vision of the self-organized network with the artificial intelligence or machine learning algorithm. We have some use cases in Vodafone for this that have some improvement, not a small number, but significant improvement for the throughput, for example, for the main KPIs for the throughput calls and CFR. I want to know your vision and your.
No, I mean, I guess you're right. There are many, I would say, niche cases where this can happen. Machine learning, as soon as you have a mismatch between our model on which we base our algorithm, there's something against machine learning. I'm not at all, I don't want to say at all that this doesn't make sense. I'm just saying are there any big improvements with regards to any metric we can achieve through machine learning that really makes a difference? And this, I haven't seen them personally. That's the point I want to make. I would be more than happy to see great use cases arising from this. I'm working on this topic, but I just want to, I'm not overly optimistic at the moment, given my work in the last 3 years.
Yes, please.
Thank you for the very interesting presentation. We see also from our point of view a big challenge to have a prediction or guarantee quality officer on the side link. Actually, I mean, on the UU link, maybe there is existing interfaces where you can request QoS, and maybe it's possible to run some algorithm on the network side, and you get it then into the vehicle. But on the side link, it is if you don't have a coverage, or if you don't control it with the or by the node or by the network, it's really difficult to find a reliable prediction on the side. That is what I want then just to comment from myself.
No, but I also wanted to say that I think that this whole question of predicting of QoS, this seems to me something which I wouldn't know how to do without machine learning. I mean, I haven't seen a lot of work in this area yet. I mean, there's a lot of work on predicting video quality, making, predict loading buffers for video based on what you think the channel is going to be, etc. These are all nice things, but I haven't seen a lot of work actually on QoS prediction. So I'm excited to see what's going to emerge in this direction. But I think this is a great use case actually to present.
Yes, please. Thank you for your good presentation. I'm very interested of your AI lady. So I'm asking, do you have any minimum requirement to assign AI lady to the system or a product? Because can we make some expectation? Can we expect 99% or 100% of accuracy? So I want to hear that.
Oh, okay. First of all, this logo, I did it by myself. It's not something coming from Nokia. There are no Nokia AI-ready products yet. I also don't know if this is a good idea. The point I was essentially trying to make is, so there's this common pain point. To any person I speak, everyone is complaining about we don't have data sets, we don't get the data we want. As soon as you would like to data from, as soon as you do machine learning, you would need data from a real product. It doesn't make sense in many cases to base it on simulation. Now, as research has this problem that I can't tell people working in product division saying, hey, can I get data from our current base station? You will tell me, yeah, we could, but you needed to specify precisely what you need. So there's no easy way, essentially, of accessing any desired data at any point in the protocol stack when you want. And I think if you have something which is close to AI ready, one would not have this pain point anymore. Essentially, if there was a way of how I could easily specify which type of data from which protocol stack, which point in the protocol stack, which device I could get, then I think it would be a truly AI ready product, because we would not need to think about how to get the data anymore. That's kind of what I was trying to say. I don't know if this answers the question.
One last question. Time for one last question. I think we had many questions, so let's thank the speaker again. And the next presentation will be given by Marwan Deva. He's with Huawei, Vice President of Huawei Fund R&D Center.
Okay, first of all, thank you for inviting me here. I'll be giving a talk on mobile AI, which is a strategy that Huawei has been building around what we call cloud AI and on-device AI. And I'm going to be open to discuss many opportunities that I see in at least AI for wireless networks. I think the thought that Jacob brought in is quite interesting, and it's true that I would say that telecom engineers have been very good in, I would say, doing some mathematical modeling of the network. And this is basically one of the things that we're not seeing in terms of gains, but I'll show you that you can have at least some scenarios where you can really gain because the mathematical, I would say, point view that we're having in terms of modeling, there's a stopover on which we cannot go forward anymore. So of course, the general thing that people tell you when they want to apply AI is that of course things are getting extremely complex. And we see it with the movement from 4G to 5G, where basically we went into, I would say, speed of race around the data rate to something more diverse, going from EMBB, URLC, and MMTC. What makes things even more complex is the fact that at the end we're looking at more on the topic of end-to-end performance. And this is something that I think wireless engineers have a hard time to cope with. There's been a lot of work on cross-layer design, trying to understand how we can cope from one point to the other point. And it ended up that it's quite difficult to understand how basically an effect of a network where there's many base stations connected, where we have a network behind, where basically we have a full IP network, can have an impact basically on the wireless communication. Usually people tell you that this is what wireless AI is for. It's basically the fact that you're using some kind of sophisticated algorithms called machine learning, which are able to basically enhance your target when the network cannot be accurately expressed with formulas. And as you can see, the big difference between what I call wireless algorithm here and AI algorithm is basically that the scope here we're having is something related to the end-to-end network. An end-to-end network is very specific. There's a, I didn't put that slide here, but there's a very specific example in our company where we have been showcasing that doing, I would say, AI techniques for voice over LTE optimization turned out to be something very well for our network. Basically, you have to know when you consider voice for LTE, this is a typical example, well, you have, of course, what we call the signal-to-noise ratio, the coverage that you're having. But the fact that you're having a good coverage does not translate immediately with the good, basically, voice over LTE, I would say, signal, or at least the performance. And why? Because basically, you're running around a full IP network, and basically, you have a protocol called IPsec. You have a lot of protocols behind, which you're not really mastering. So modeling the end-to-end performance, when you have a wireless link plus behind, I would say the network behavior turns out to be very complex. And those cases were fruitful in terms of doing things. Now, something very important also about, I would say, this machine learning algorithm is that we're also running from, I would say, behavior, because we can afford it, from compression to data. And this is quite something important. Usually when you ask somebody to start understanding how to shoot a ball towards a distance, this is a very good example that I can give you. Well, what you would do is try to understand what we call the gravity Newton equation. And basically, once you have this formula related to the Newton equation, then you can link basically the angle to the distance. And whenever somebody tells you to shoot at a given distance, you can find the angle. The other option that you can do, and which works quite good, is basically to shoot like hell many times, distance angle, and you have a big table telling you whenever you shoot, this is the angle you have to choose. So basically, next time somebody tells you to shoot a certain distance, you just look at the table. Of course, you have enough processing power to do it. Data mining algorithms, regression, what kind of correlation you can do behind, and basically you can find the angle to which you choose. So this is basically the mentality that people are having now in, I would say, in the community of wireless AI, is basically instead of having those very sophisticated models, when we can, we're happy to have them, but when we cannot, well, basically this is an approach which solves your problem. Of course, I will not talk about the energy problem, which I think could be a discussion for this focus group, is that these technologies that we're using at the moment, blockchain, AI, artificial intelligence, are consuming a lot of energy compared to the classical methods we have. Typically, if you look at the AlphaGo, people have been simulating between the guy who's playing the AlphaGo and the machine which was playing the AlphaGo, basically, you had the 10,000 times, I would say, dimension in terms of energy. And I think this is basically one of the big stopover of this technology because we're wasting a lot of resources to be able to compute the same thing that we used to do. But however, when we don't have a solution, I think this is one approach to do it. Now, if you look at what people are proposing in terms of AI for wireless, well, you have a bunch here of techniques which people are trying to use and the applications behind. So basically, as you can see, it goes from high-frequency, low-frequency collaboration to PAPR nonlinear compensation because we don't really understand how things work, to also self-operation of networks, to basically also some map reconstruction that David showed previously to failure detection. And all these techniques depend also on the time frame we have, basically going from the RTT, resource, when you have it at the radio level, or the time symbol, or the radio resource management level, and you go up. And at the moment, of course, we're embedded in the cloud where a lot of people are proposing different techniques. We're seeing a bit of enhancements, but the biggest enhancements are always when we don't have any kind of model to understand what's happening. And basically, as I told you for the shooting things, that's what you should do. Now, before we continue, I'd like also to stress that even though we're doing a workshop here on AI for telecommunication, the notion of AI for telecommunication is not new, okay? A lot of people bring it from the computer science field, but there's a famous paper of Shannon from 1949 called Programming a Computer for Playing Chess. And I think that paper is very interesting because if you read it inside, this is taken from the paper, you have some use cases that already at that time Shannon was trying to cope with by using machine learning. And of course, the idea was using machine learning up to the physical layer, where you use machine learning for designing filters, because basically it's quite complex, you don't know how to do them, equalizers, designing relay and sequence circuits for doing routing, and I think this is something that in terms of SDN we're doing quite good at the moment, performing mathematical operation, translating one language to another, I don't know what's skipping every time, capable of strategic decisions, of orchestrating a melody and logical deduction. One thing which is very interesting is also the notion of deep is also there. He tries to explain how you could build an AI machine, and of course, what you have to do is consider what I call the number of deep moves that you have to do. And one of the stopover that we had at that time in a paper that is well, I would say, showcased is the fact that we don't have enough processing power to do it. Okay? And this is, I think, the big gap that happened from that time. Of course, people continued in that. There's also a couple of papers going in the 90s trying to come back to those ideas. There's also a paper dating from 2005 called Cognitive Radio, Brain in Power, Wireless Communication, where people try to build up what we call a wireless brain. So the notion behind is not new. We'll see what made the big change. So if I take, for example, this paper of Simon Hicken, which basically tries to do what I call cognitive radio, what was the idea? Well, the idea is to build up learning algorithms. And from that idea, of course, a lot of people started to believe in what I call self-organized networks. You have to know that there was a big trend of research from 2000, I would say, 3 to 2014 called SUN, where the idea is to say, well, basically, I could build up learning algorithms where I have an entity here called the user, which basically will start transmitting towards another user or another, I would say, base stations, and I will learn based on my feedback. Okay, and this is exactly the status of learning, basically, because basically you see the action, then you update your reaction. And how you do it, basically, well, it depends on the parameters. It can be your tilting of antenna, that's one case. So you could use SUN for tilting. It could be also the power allocation that you can do. It could also be what they call the delta MCS, meaning basically when you have an MCS from going one level to the other level, in general it's fixed, but you can adapt it according to what you learn basically on the environment. And what you can show, of course, is by doing these techniques that people have showed that, well, you converge to some kind of equilibria, which showcases you that you can build SUN algorithms. And it turned out that we could build those SUN algorithms. And you have here a bunch of, I would say, before this AI trend, which happened, where people have been working on algorithms like best response dynamics, fixed display, reinforcement learning, true utility strategy learning, trial and error learning, regret matching learning, Q-learning came up to be quite famous, multi-arm bandit, and imitation learning. These are all algorithms which were available already from 2005 to 2014 in literature. One of the main reasons why it didn't go through, well, basically, everybody got stuck into this what we call exploration versus exploitation dilemma. What it means basically, well, to learn, it takes you time. Okay, and we are in mobile environments where basically by the time you start learning, you need to learn the number of users around you. You need to learn the kind of utility they want to maximize. You need to learn what kind of actions they want to do. And basically, depending on what you look at, it takes a bit of time to do all these, I would say, learning algorithms where we have brain-empowered intelligence embedded in your device. Okay. Now, of course, what changed? Well, three things changed rapidly since 2014. First of all, we came up with more sophisticated machine learning algorithms. I'll talk about them. This is quite important, especially this deep learning, I would say, era that happened recently. The other, which is the other big importance that people tend to forget, is the computing capacity, which made it available. We ended up in saying, okay, instead of having Maxwell equations, let's have all the data generated by Maxwell equations and use that. Why? Because basically we have enough power and we have enough resources to be able, instead of computing the Maxwell equations, just use all the data generated. This is, of course, from an energy point of view, a big nightmare, but it turns out that since we have or we can afford it, why not? And the other thing is the massive amount of data that started to be available. Now, of course, with big data, we ended up seeing that we don't necessarily need to learn by ourselves. We can learn, of course, from our past experience and also the past experience of others. And this is quite different. I'm not just iterating on myself and every time seeing my action, but of course, many people have been doing it. Many, many people. And I can leverage all that information that I gather from all the experiences of others to be able to do it. And from that, as you can see, there's a whole trend of algorithms which can exploit all the available resources from the learning experience, not of my base stations in germ tilting, but all the others. So for this, of course, there's two things then you have to do. And this is what the big trend is at the moment in networks, is where do you compute the AI aspect? I know we're jumping every time. Okay. No, it's okay. Okay, I don't know why it happened. Okay, it's okay. So in Huawei, we've been working on this notions of how to compute AI. And recently, we've been looking at a strategy called mobile AI, where the ability to at the same time do a centralized computation of all the experiences of the people, but also on the device. And it's called on-device AI. Why we are looking at both aspects? Well, basically on the device, as you see, we have a lot of constraints that we cannot be coped with the fact that you aggregate all that information across a central entity. The main reasons are, of course, latency, where basically because of latency, you cannot bring back all the data that you have gathered. The other, of course, is also what is related to connectivity. Mobile device is not always connected to the network, and if it's not connected, well, basically it still has to be intelligent. When you go on an airplane, even though you don't have a connection during those 12 hours of plane, you have to do it. Recently, Huawei released in our Mate 10 a product called Kirin 970 for information, which embedded a neural processing unit, which is basically a specifically targeted chip which can compute, of course, AI algorithm. And I'm going to give you here, when you have these things, what kind of things you can do. When you can have an on-device AI and a cloud AI, what the opportunities that you can leverage from a telecommunication network. Let's see, for example, the biggest problem that we had in Sun, basically, in terms of speeding the learning process and making Sun happen. At the moment, of course, when you're looking at basically learning problems, the idea what people are pushing, and David talked a bit about it, is this collaborative AI aspect. Basically, how without any detailed modeling of the overall system can AI-based users learn and interact without data exchange. And here, basically, what you can do, well, you can leverage, of course, your knowledge of the data that you have, but also take into account basically the experience of the other and basically exchange models that they have been learning and improve your modeling ability. You have to know that this is a big trend in research at the moment called federated learning. There are many people working on this. Here I'm going to talk about imitation learning, which is also one of the classes that we have of collaborative aspects, which enables you that. Let's take, for example, this case, which is called user self-association. Simulatory learning, federated learning, all these imitation learning all come from the same thing. So let's take a typical example that you have here where a user wants to connect to a base station, which is a classical problem of user association. And you ask yourself, well, how can I speed up the process of learning how my users in the system in a decentralized manner can associate to the different base stations? Well, one way to do it is to exploit similarity between users to reduce the communication load between users and make the decision. Why? Because if users are in the same conditions as me around, and they have the same model, then basically I can benefit from that model with my local data from what I'm learning to be able to link to a base station. So here, let's take the example. Each user has to choose the best small base station among its options. After selection, we'll receive a reward based on the congestion level of the SBS and the channel gain between itself and the SBS. Each user tries to solve an optimal control problem for selecting the SBS over time. And I'm sorry, why it's jumping? Maybe you can stop it. Yeah, it stopped. Okay, good. Otherwise, I'll just be keeping going back and forth. Okay, so let's see, for example. Okay, now it's not moving anymore.
Maybe I can.
Okay, next slide. Yeah, can I stop it this way? I don't know. Good. So here, let's take an example and to show you how you can put forward these techniques. You have a user for which the biggest importance for him is to connect to the base station, and connection is related to exactly the rate that he can access. Okay. Of course, there are other users who can connect. And then there you have a penalty, which is an effect of the congestion on the SBS, which is related to the total number of users that there are in the system. Next. Good. Then, in this case, what you have to do is basically use at the same time the fact that the user, that the user basically connects to the base station. This is what I call the reward. But then you have also a mimicking system, which basically tries to optimize the fact that how you select yourself to base station. This is the STX, where T is your over time and X is yourself, towards your neighbors, which are the other neighbors at time T, and Y, which are different distances. And you try to mimic basically this distances in terms of similarity. Of course, the similarity has no reason to be something related to a square distance. You have a factor called G there, which is a Gaussian kernel, which you also learn basically because the fact that you learn from your neighbors, this is the model exchange, which you use in techniques like federated learning. This Gaussian kernel enables you to learn how you do it. Go back again. So of course, these techniques, just to give you an example, relate to something called mean field gains that we've been trying to use in our company. And this is very reminiscent of a work that some mathematicians have been using also to explain how the Mexican wave behaves. Here you have the same kind of equation which appears. As you can see, if you take a user in a given stadium, the V is his altitude, T is his position, and T is time, and X is position in space, while ZT of X tries in general to be very similar to your neighbor. You try to behave exactly as your neighbor in a stadium. However, this is the minimization of the first term. The second term, which is F of Z of Tx, is basically the penalty that it costs you to be up or down. If you're up, it costs you. If you're down, basically, it doesn't cost you energy. And then it costs you to move from a given altitude, which is 0, to a certain altitude. This is the speed at which you vary. So if you try to solve this equation, you get exactly how a Mexican wave behaves in the stadium when everybody starts standing still. Because basically there's a mimic behavior where you inferred from the guys around you how they behave, and then you added, of course, a constraint. And this is exactly the type of things we have been doing. Go on the next slide. So at the end, without going into details, I don't know why it's not written well, you have two types of equations which end up solving your problem, called the Hamilton-Jacobi-Bellman equation and the Fokker-Planck equations for the evolution of your network. Go on the next slide. You can solve it in a discrete way by using something called the Markov decision process, when you try to approximate the different techniques. I will not go in detail. What's very interesting about this, next slide, is basically the convergence rate. We took users with SBS, what we call small base station in a given simulator, where you have 20 imitator users and 20 non-imitator users. People who use AI in device to learn, and others who don't, basically. And if you go on the next slide, you see that between the two, of course, you have your system which automatically will decide on which SBS small base station you will connect to. But what's even better is the fact that you can speed up the convergence by exploiting and leveraging all the different, I would say, data of all the other users without exchange of data. This is very important. We're not exchanging data. This is a very good trend at the moment. We're exploiting the models that the other have learned by seeing basically how they connect. But we don't exploit the different features of the data And you have to know now these techniques are getting a bit more and more, I would say, applied for people who are using it like Google in pictures, where basically you don't want to exchange the pictures with the others, but basically you learn on your own device, and then basically you provide the model of the ranking of your picture, for example, to your neighbors, and they go on like this. Okay, another point also, when we have been working the last 2 years, this is also another example. I should have put an example of voice over LTE to give you, but it's called wireless caching. So I think some of you are quite familiar with the notion of wireless caching, where basically the idea, and I think there were some presentations just before us, showcasing that if you start putting a bit of data on the edge of your network, then you can improve, I would say, the quality of experience of the user. And one of the big problems that you have to do that, well, basically you need to predict a bit more the kind of data the user wants, and also the location of the users, because otherwise you don't get. And this is also a big trend at the moment in the research, I would say, arena of trading what they call bandwidth for memory. Basically, people are telling themselves, well, if we can embed our small cells or base stations or mobile phones with more and more memory, and memory is cheap, then basically we could increase basically the kind of bandwidth that we can offer to the users, because basically we can predict. Next slide. So here, well, basically what the big thing that you have to do is to predict the content request distribution and mobility pattern of each user. And if you can do that, of course, then you can enhance the quality of experience of the users. So it's not specifically targeted to the RAN, like Jacob was saying, but basically it takes into account at the same time the kind of data that is running in the network and the mobility pattern of each user. Next slide. So what we did here is to apply things related to machine learning which take into account the timestamp. Okay, and for that you need some tools related to the fact that you don't use machine learning only in the dimension of data, but also in the fact that it runs across time. Eco-state networks is one of the tools. You can use many other tools, but eco-state networks are very nice, have nice features because they're easy to train and they're good at dealing with time-related data. So you apply it in the two cases, and just to showcase you that you can have some quite important gains. Next slide. Okay, this is for people who are not knowledgeable about eco-state networks, is that basically to optimize them, they have some very good features in terms of optimizing the parameters. By the way, this goes back also to the point of Jacob, is that the big problems with these techniques is that we cannot understand why they work. In general, when people ask us, we just tell them these are the weights. So these are the weights and you're happy with them. But we're not able to really understand why it works. Go to the next slide. So basically what you do, you start doing some learning on the content distribution, where you have agents which are the base station devices. The inputs are the user's context, including context request time, gender, occupation, age, and device type. And the output is the content request distribution. And then you have what we call an eco-state network model with an input weight matrix, a recurrent matrix, and an output weight matrix. Next slide. And then you have a training called the dynamic reservoir, for people who are familiar with that, state update, which is a function of these weighting matrix. You have an output, and then you have also what we call an output weight matrix, in which you can run your algorithm to be able to weight your data. Next slide. You do the same for the mobility pattern, same philosophy, agents, inputs, which is the current location, okay, output predicted location, NESN model, recurrent matrix, input weight matrix, output weight matrix. Same technique for the mobility this time, dynamic reservoir state update, output, and output weight matrix update, the same philosophy. And then you can run your algorithm of ESN to at the same time do the user location prediction and the data request prediction that you can have in the network. Go on to the next slide. So we've been applying that, and we had some colleagues from the Beijing University of Post and Telecommunication, which did some measured mobility patterns with the data and also with mobility. And we've been applying those measurements of data that we had with real data from Youku to predict. You can find these results in the paper that I cite. And we took a network on which we could build that to see at least the impact. And if you go on the next slide, what's quite surprising is that as far as the mobility prediction is concerned, and as far as also the kind of request data is concerned, you have some very good match between what the exact predicted and the real, I would say, mobility patterns of the users in both of the cases.
Sorry, Marwan?
Yeah, I'll stop here.
No,
okay.
Just
Here also you have some simulation results showcasing the curves that you have between the two kind of results, between the number of users and exactly the gain that you have in terms of effective capacity between the optimal caching that you do, the SN caching, and also the techniques which are related just not without caching in these two cases. I'll stop here. I think my presentation finishes. So it was a good time.
Excellent. Okay. Thank you very much. Yeah, well, thank you very much for this very interesting talk on the hard circumstances. We have question for one question. Time for one question.
Of the slides.
Well,
Jacob,
please. Hey, yeah, thanks very much for this rich of this presentation. I just have a question about something I also mentioned concerning using machine learning essentially to learn how to play, exploring.
Yes.
What's your view on, would anyone let you experiment with a real network to learn how to optimize it?
Well, basically in any case, let's say the classical ACNAC system is already a learning system. Basically, when you have a device, basically, you try to learn at which rate you're going to transmit towards a receiver. Well, basically what you're going to do, you're going to transmit at a certain level, and based on that, you're going to get a reward, which is an ACNAC. If you don't have, then you're going to reduce it. The problem with this technique that we used to do is that, of course, the learning process, the exploration time is too long, because basically you don't have enough data that you gather. But then what you can think of, and this is the example I was saying, is that if you start gathering all that information in a given database, which is your mobile, and doing it all the time, and then you gather and then start exploiting, because we're not exploiting all the past experience that we're having. We're doing it on the fly and say, okay, I start my communication. But I think mobile devices in the network, if they can store the data that they're learning within a couple of weeks, months, you can enhance the network. This is my thought.
Okay. Yeah. I was kind of expecting. I was kind of expecting that in automotive industry, there are now essentially every company seems to develop simulators to simulate essentially cars, to be able to simulate essentially millions of years of autonomous cars.
Yes.
I was actually wondering, in telecoms, in order to avoid learning with a real system, don't we need like essentially a digital sibling or clone of a real network in which you could simulate years of traffic to apply these methods in order to essentially avoid the problem that it takes too much time to learn?
This is one option. The other option is all these techniques like AlphaGo has been doing is that, this goes to your sibling, is basically, AlphaGo went to two stages. First of all, they used a lot of games on which the AlphaGo played, and then of course AlphaGo played by itself. They gave it the rules,
yeah.
And this is exactly what you're saying. You're trying to define the network with the rules, and then the network plays by its own, and then basically after a certain time, you have all the learning process, and it works quite fine. So this is of course another approach. Instead of starting with all the huge, I would say, learning process that you do in real time, and you play. You have some rules and you play by yourself, which is basically what you're saying. You create some kind of sibling with the rules, but you need to define the rules. This is, I think, still a bit complicated because, as far as I see, of course, we're designing the network, but sometimes on a whole scale, we don't really, or at least we are not able to really cope with the whole big thing when you look at the end-to-end, because it's not just about wireless WAN. It's the whole thing. There's the server behind, the latency, where they're positioned. It's a whole big thing, and then it gets a bit complicated. Question? Yeah, question. Yeah.
Well, it's kind of question, comment, and also can open some new topic for this focus group. I'm just coming from an MPEG meeting. MPEG is mainly about compression video, as you can know. And there is new topic about compression of neural networks and finding some coded representation of neural networks. It started in MPEG mainly from the video part because we are using that for search and video analysis. But when I heard you talking about federated learning, exchanging models in the network, it's raised in my head that perhaps this kind of new representation could be very interesting for these focus groups, especially this morning I heard about standard models, representation, etc. So very quick question, perhaps we can continue later on. Is this kind of models generate really a lot of the data in the network and can justify some coded or compressed representations, etc., or at least standard representation, not necessarily compressed?
That's a good question. The idea of federated learning comes just from the whole framework of doing distributed learning. It's how you do learning on distributed databases. And the idea is if you don't want to do exchange of data because you have privacy constraints for people who work on images, for example, you have latency constraints and you have other type of constraints for connectivity, then basically, yeah, it's representation of his databases that is exchanged, and then instead of starting from zero when you learn, you start from his model, and then you build up a refined model, and then you exchange a model to your neighbor, and it goes in. So yeah, there is compression if you want in it, but yeah. In any case, I think this is the way to go because I think the main 2 points that the focus group has to put here is the huge amount of energy that these techniques are using compared to classical techniques that we're using, and I think we have to study basically at what point there'll be a stopover because we cannot anymore, cope with the fact that instead of using models, whatever they are, even if they're not great, we should be able to incorporate them. We just decide to use the data. You take the blockchain, for example, which are all these new technologies. I think they're totally irrational in the energy. The total energy that is consumed by the blockchain per day is exactly the consumption of Ireland per day. Just it gives you the amount of when people do mining. Here in the same thing, I think we're going towards a tendency where because it's cheap, let's start computing all the things. The second point I think which could be put in the focus group is what Jacob said. I think we could start thinking of not a 3GPP model, stuff like this, but some kind of, like you said, sibling thing where people should be able to test. So I wouldn't call it a 3GPP reference for the network in terms of modeling, but some kind of reference, I would say ML reference model where everybody agrees on, where you can generate the data there, and this could be of use for everybody. And we all agree that the data is generated by that thing, and whenever somebody solves a learning algorithm and works there, we say it's good. And we're all agree that that super generated model is what we agree on, all of us. Yeah.
Okay, thank you again. We need to move on. Thank you again for the talk. Next presentation will be given by Wojciech Stanek. He's with the Fraunhofer of HHI, leading the research group on video analytics and machine learning.
Thank you very much. I'm very happy that my talk is scheduled in this slot now because all what I have to say is kind of related to the discussion and to the previous presentation. I'm also think, and I hope I can convince you that we all in this focus group we not only need to think about technology, network technology, but also about machine learning methods, requirements of machine learning methods, and I think compression of the machine learning methods, because if you want to use deep learning, machine learning in communication settings, we have to deal with new challenges, and I will talk about them in my talk. Okay, so today's AI system, as you know, are very good at solving very complex problems like playing chess, playing AlphaGo, poker, or doing some analysis of images, medical content, or like recognizing traffic signs, or image classification. And the reasons for that have also been mentioned in the previous talk. So we have huge volumes of data, millions of labeled examples with computing power, which requires or has a large power consumption, as you can see. It computes things highly parallelized, and we have access, we have trained powerful models like deep neural networks, which these numbers are the most extreme numbers I found. There have been some DNNs with billions of parameters and thousands of layers, but of course, even with those extreme numbers, the models used in practical applications in image classification settings, for example, are also quite huge. And one must also say that the architectures which we use, like the convolutions, max pooling layers, and so on, are pretty adapted to image data, speech, text, and actually these applications where these models are highly successful. And the point I want to make in my talk is that the communication setting is kind of a bit different. So it has additional requirements which or additional problems which so we cannot just simply apply these methods which are successful in image domain to communication settings. I mean, in communications, as was mentioned in the previous talk, if you want to implement things on a smartphone, for example, you have to think not only about the performance, but also about the size of the model. So you cannot execute models which requires gigabytes of memory or which requires a lot of energy because your power supply is very limited in some IoT or smartphones or communication, satellite communication settings. So you have to think about efficiency, and you have a bunch of other additional requirements. For example, what's called federated learning setting. Before data is often distributed, you are not allowed, or you don't want to gather data in a central server for privacy reasons, for example. So you need to find ways how to learn in the distributing settings. So how to enable learning in the distributing settings. And this is, I would say, I mean, a problem which is kind of linked to communications, which is which hasn't been so far tackled in these other applications. Data is highly non-stationarity. The communication channels may change drastically over time, so you need to adapt. You need models which are adaptive, or you need to define mechanisms which can deal with that. As I mentioned, you have restricted resources, you have restricted memory, you have restricted energy, power supply, you have maybe also restricted operations. Certain architectures, certain chips just allow integer operations, maybe not floating point operations, and you don't have these restrictions in the settings which are shown here. You have communication costs if you exchange information between agents, between different devices. There is a communication cost which are assigned with this information transfer, and of course you have limited bandwidth, so you need to keep this cost as low as possible. In communications, interoperability is a very important issue. So your system has to interact with other systems. So you need to define interfaces. You need to define formats for the data exchange, for the model exchange, so that every model in the communication framework understands these formats. There are security privacy issues, as was mentioned before. There is the interpretability issue. I will talk about this later. Many people think or regard deep neural nets as black boxes, and it comes with a lot of problems, and I will talk about this later. And there is a recent problem also on trustworthiness. People showed that you can easily fool deep neural networks, you can attack them, you can finally change, add noise to images so that a human is not can see the change, but the neural network is fooled. In an autonomous driving setting, what people demonstrated is that they can fool a traffic sign recognition system by just putting on some stickers on the stop sign. So if there is a sticker on the stop sign, the system doesn't detect the stop sign anymore. So these are all issues which we need to deal with, and we need ML techniques which are kind of adapted to these issues if you want to apply machine learning in communication.
And it's not only about the algorithms, and I don't want to say that we need like to develop like completely new algorithms, but we also need to think about protocols, data formats, frameworks, mechanisms, how to tackle those things in practice. So, for example, the trustworthiness issue, maybe you cannot defend against this adversarial attack completely, but maybe you can define some mechanisms so that you can detect some attack, or you can defend against them under some assumptions. And I think this topic needs to be studied also in this focus. In the next slides, I will just briefly mention these two topics: our work on how to deal with restricted resources, and how to make neural networks interpretable, how to explain predictions of neural networks. Okay, so as I mentioned before, deep neural networks have millions of weight parameters, large size, energy hungry in training, but also in inference stage. You usually don't have any restrictions on the operations, so you allow floating point operations, and all these can be like in communication settings. These things can be difficult because you may have some restrictions on the size, on the amount of energy you have, and also on the operations you're allowed to perform. Therefore, many people in the community, in the machine learning community, realize these challenges, and there have been some recent work on compressing neural networks, and I think very interesting work by one approach is by weight quantization. So in order to for example, reduce the size of a neural network, you apply some quantization algorithm, so some lossy quantization, but you still make sure that the distortion you introduce by that is minimal. And you can reduce the size of a neural network and the complexity by quite large margin. So how does it work? And what people did is, so they have some weight matrix, then they apply some quantization motivated from weight distortion theory, then maybe they arrive at this quantized matrix where they sparse matrix, so they have a lot of zeros, so a lot of connections are kind of not important for the neural network. And then, I mean, instead of representing the matrix implicitly, they use some like standard format for sparse matrices called compressed sparse row format, which is quite common in the field. And you can reduce the storage size if you want to, for example, exchange neural networks in communication settings. You want to send a model like from one agent to another. You can reduce the size of this weight matrix by quite a large amount. And the good thing is also that this compressed format also allows some fast multiplication. So you don't need to reconstruct the matrix to do the inference. You can also do it in the compressed domain. And this is how you would represent this matrix in the sparse data format. So you have some notion on which weights you have, like 4 and 2. Like 0 is the most you can skip because this is the most it's kind of the rest which from your encoding, and you have the indicator vector where you indicate at which position this particular weight belongs to, and this is kind of standard sparse matrix format, sparse matrix representation. And the question we ask ourselves is, can we do better? Because I mean, and actually, yes, you can improve the sparse representation by some amount. And the idea behind this is that this sparse format, I mean, the network, if you compress neural networks by weight quantization, it does not necessarily lead to sparse matrices. So you have a lot of we call this weights with the same value, the weight sharing property is induced by this operation, but it's not necessarily a sparse matrix. And and if you have like this property that a lot of weights have the same value, you can do a trick. So instead of doing this in neural networks, you always need to do this multiplication. So you multiply the weight with the previous activation of the previous layer and sum it up. And if you know that like many weights have the same value, you can just take them out of the sum. So you have like weights which have like same value, so you don't need to multiply them over and sum afterwards, but you can take it out of the sum and then sum first and then multiply. And it saves you a lot of floating point operations. So it saves you a lot of energy, and I will show you some examples in a minute. And if you apply this trick, you can come up with a more efficient encoding for matrices, and we call it like I mean, I won't go in detail over it, and our paper will appear soon on Archive, where all the details are written up. And but the idea is that you have like not only like one indicator vector which indicates at which position this weight is, but you have like multiple indicator vectors and some pointers which relate. So we have like a double two-way indication, and this saves you some space. So you can more efficiently encode these matrices and compress the neural network much better. And here are some results. So we tried to compress like the VGG16, which is a standard neural net used for image classification, for example, and it has around 550 megabytes if you save it like a typical format without any compression, and the accuracy is like around 68.7. And if you like have a standard prediction, you have like a couple of million operations which you need to do, floating point operations, and there is an estimate how much energy you need for one floating point multiplication, and this is kind of using this estimate. So we estimated that for like one prediction needs like 70 millijoule energy. I'm not. This is just like assuming that this estimation which we use is appropriate. And just for information, here is the total energy of the iPhone 8 battery, so you can compute yourself how many operations, how many classifications you could do with such simple architecture. And if you apply state-of-the-art compression technique to this neural network, so you compress it and you use the sparse format, you reduce the size of it like by a large margin. So instead of having 550 megabytes to transmit, you need to just transmit 17 megabytes without any loss in accuracy, which is a nice thing. And you also like to reduce the number of floating point operations. And if you go one step beyond, if you don't use a sparse data format but you use the format we proposed, you can save even more space, and also reduce the number of floating point operations further. So we think that, I mean, this is just like one proposal, one format for neural networks which we developed, which allows to have like small models, also like reduces the number of energy you need to compute these models. And I think especially in this mobile AI settings or in communication settings where you need to transmit models over wireless channel, this is quite important to also think about how to reduce information, how to represent these models without any loss in accuracy. And I think this is a topic which fits quite well to this focus group. Second topic. So many of you mentioned that neural networks are black boxes, and the prediction, you don't really know what's happening and why this image was predicted as rooster, for example. And I mean, this is a big disadvantage because optimally you would like to verify your prediction, especially if it's a medical application or in like autonomous driving. You have to make sure that the system works as expected. It has also some legal aspects. There is this right to explanation, which was established by the EU. And of course, if you know the weaknesses of your system, you can improve it, or you can learn new strategies. For example, in Go, the system kind of came up with a new strategy, and if you understand why it plays
So in a certain way you can learn from it. And actually the good the take-home message for you maybe is that there are methods available for explaining neural networks. We have proposed a general technique 3 years ago, 2015, where one of the first in this direction are now currently writing a book on this topic, organized this workshop, and we'll have a tutorial at CVPR this year, which is the largest computer vision conference. And what we do, I will just briefly mention the idea. We kind of decompose the prediction. So what our method does is tells you how much each pixel in the image, how much its input variable has contributed to the prediction. And we can visualize this as heat map, where you see, like in red, you see the pixels, the area which has contributed quite a lot to the prediction, according to the neural network. And I mean, and it sounds like a bit maybe, okay, so like heuristic, but actually there is a theoretical underpinning, which is our method is related to Taylor decomposition of the neural network function. It has there is some theory behind it, but I will not talk about this due to time constraints. Just like maybe like the basic idea. So we have like a prediction step where the network says, okay, it's a rooster, and then we redistribute this evidence for the rooster back to image space according to some rule which has some theoretical underpinning. But I want to show you some results. So here you see, like, we trained our neural network for classifying handwritten digits and asked our method what makes this image a 3, and it tells us, okay, because there is something missing here, it's a 3, which makes intuitively sense for a human, because I mean this is a feature which distinguishes, for example, a 3 from an 8 or a 3 from a 9. And we also ask ourselves what makes this makes this digit a 9. And then our method tells us this is not a 9 because there is evidence speaking against it. So you see the blue part, which says that if it would be a 9, there should be something there, but there is something missing. And so this simple example visualizes like what the method is doing. And I want to give you like few more examples on some real data. So there is like an image classification. There is like a challenge where people submitted like every year like some tested their methods on. It's Pascal VOC data. It was challenged like I think the last couple of years before ImageNet. It was a standard challenge, and the Fisher vector SDM classifier was one of the winning methods at that time, a couple of years back. And we wanted to see what is the difference between Fisher vector classifier and state-of-the-art neural network. Of course, overall, the neural network outperformed the Fisher vector classifier by a quite large margin, which was not a big surprise for us, but for the cloud force, both are almost on par. And we wanted to understand, do they actually perform the same strategy to detect horses in images? And actually not. So if you can see a heat map from a Fisher vector classifier here and the DNN really looks at the horse, at the horse back. And in this particular image, whereas the Fisher vector classifier focuses on some area here at the bottom. And if you look closely, there is some copyright tag. And a lot of images in the data set had this copyright tag. And this, because these images from horses came from a website from some horse website. And people, over the years, they didn't realize it. They just like published them, the results and compared the methods, but they didn't realize that their models are learning something strange. Because in this case, of course, it was the data's fault. The data was biased, but if you have like thousands or millions of example data, training data, you cannot go over each of them and test it for such bias. This was one example. Another one deals more with state-of-the-art results. So we trained a neural network, which we presented at last year's ICCD conference, the biggest international computer vision conference, for age and gender prediction. we got state-of-the-art results on the data set, and we wanted to know what makes a person young and old. Here you see like example of two ladies. The above one was predicted to be in the range 25 to 32, whereas the lady below was classified as 60 plus. And you see that obviously, if you look at this blue area, it seems that the network learned from the data that smiling speaks against being old. So that old people don't smile. Whereas like this lady above like smiles, and you see that like smiling is a feature of which supports this classification. And this sounds maybe a bit funny, but if you don't know what your network is doing, what your network is learning, this can happen. I mean, and also in communications. I don't have any examples from communications, but if you feed in your communications data to the neural network and you learn something, then maybe something strange happens, and you need interpretability to know what's happening and to understand what the network is doing and why it classifies people or like users in a certain way. Third example, this is like, you probably know this Atari games with DeepMind. Like DeepMind had a paper on that where the neural network learned to play Atari. And the funny thing is that we visualize the strategy of this neural network, and it's a bit hard to see here, but we saw that like there is this game Pinball, and the neural network didn't really learn to. You can control the ball by controlling like this things like to shoot the ball, and this is not the strategy the neural network learned, because in Pinball there is another strategy you could do. If you control the movement of the table, you can move the table slightly by pressing like this by pressing the press button. The table moves a bit, and in this Atari emulator, this behavior is explicitly like also emulated, and the neural network didn't control the ball by playing like this handles, but it controlled the ball by shaking the table a bit. And this is also a behavior which we didn't expect, and I mean, this also shows that how important interpretability is, and also like what Slavomir mentioned before, that in communications and real systems, we may need to have hybrid systems. We may need to have systems which learn from data, but we may also want to bring some human intuition, some expert knowledge to avoid these behaviors, which just from the objective of performance may be good, but from the strategic point of view, what we would see as good are not appropriate. So there is also like this saying that your method can be right for the wrong reason, and we don't want this. We want our method to be right for the right reason. Okay, so let's come to the conclusion. I hope I can convince you that if you want to combine machine learning and communication, it's not only about technology. You also need to think how machine learning can deal with these new challenges which are there. These challenges are different from challenges which are there in image domain or in NLP. And AI systems can behave differently than expected, and you need interpretability to verify the behavior. I think it has also like large social implications. For when I think of AI for Good Summit, I think this is also a very important topic which also would fit there very well. And the third point is that we need, as said before, also best practices, recommendations, and reference framework, reference presentations in order to have such a label AI ready. It's not good if like everyone trains their network in different ways, and we need some kind of recommendations also on the whole system, training, on protocol performance, and so on. Thank you for your attention.
Thank you, Wojciech, for great presentations. We are a little bit behind time, but question, please.
So one question is about the quantization part. So maybe I get it wrong, but it seemed that as if the reliability increased with the quantization, right?
Yes, a bit.
So what, is that due to some other constraints on the computation?
I think this may be due to overfitting effect.
Okay, so basically it's even better actually to it's better. Okay, so you are saying basically it's better actually to lose some of the information while learning. I mean, this is quite interesting actually.
Yes, I think this can be a regularization effect, which you, if you quantize, you avoid some kind of overfitting. But we are not totally understanding this. I think it's a nice. Also from a theoretical point of view, it would be nice to understand this more, but I think this is just like some regularization effect which avoids overfitting.
About the second part also, so when you do the kind of this interpretation, so the parts that don't kind of show up in that colored heat map, so if you remove those, does it mean that you can still get similar kind of reliability, like the performance?
Yes. So what we did, we used this idea for testing how good our method for identifying this important part is, because we call it pixel flipping. If you flip the most important, if you destroy information at the most important places, the classification drops by quite a large amount. If you destroy information at the not important places, the classification drop will be much smaller. But of course, at some point, it will also drop. So, yes.
Well, we don't have time, but okay, one more question.
Thank you, Chairman. Thank you for your good presentation. So you raised two problems, restricted resources and interpretability. I also agree with both of them. But for regarding the second problem, interpretability, I have some concern is that is related to network itself, because it kind of the generalistic problem of the machine learning or deep learning. Because if we deploy the deep learning into network, if we get the result and it works, but we don't know how it works, because it is the naturality of the deep learning. So if you want to research or investigate the interpretability in ITOT, so in this focus group, so it's the best place, because to solve the problem, we need more expert that kind of area. So it's not easy. So I want to hear you. Thank you.
Yes, I mean, I just wanted, with my talk, I just wanted to raise this issue, and I think it may be interesting for ITOT, maybe not for like as a general topic, but tailored to communications. And if you can bring together like experts from communications and experts from machine learning interpretability, and if they can, I mean, for example, if I would apply this method to communications, I would be really able to judge if this behavior makes sense or not. So you need also some experts in communications to judge this, and I think like visualization of the behavior is only like the first goal. The second goal is how can we control like what the network has learned? How can we incorporate this prior knowledge, this expert knowledge, and how can we force the network to do the right thing? So I think these topics are still a research topic, but I think it may be interested also to this focus.
I'm very sorry. We maybe can talk during lunchtime. We need to move on. So let's thank the speaker again. The next talk will be given by Hamila Rida. He is a full professor at Qatar University.
Thank you, Mr. Moderator. So the talk that I want to give today is related to machine learning application for the 5th generation network enhancement. So first of all, I would like to thank ITUT, Madame Reem Brahsin, for the invitation to provide this talk. She's Vice Chair of ITUT, I think under Group 13. So these are the outline of the talk. So the first question that comes to my mind, where we are heading with these new technologies that are emerging. And then I would like to talk a little bit about the 5G requirements, then the 5G open issues and trends, brief review about machine learning, then what are the challenges for what are the machine learning for 5G challenges, then some application of machine learning in wireless networks. Finally, in the summary, I'll try to talk a little bit about the challenges and some research direction. Here I highlight in this graph the number of mobile subscribers that is forecasted for by 2022, just for the LTE system. It's going to be about 5 billion users or subscribers. And if you look for the overall different networks, we are going to see around 9 billion. This is the projected number for 2022. This is for the different type of networks. If you look to the IoT, number of devices connected to the cellular networks, by 2016, we reached around 0.4 billion users. And the forecasted number of IoT devices connection by 2022 is going to be around 80 billion. So this is tremendous amount of devices connected to the networks. And I think here, by also 2022, we expect around 29 billion devices connected to the network. How can we handle all this amount of devices, users, in addition to the traffic? In addition to that, the question that I want to ask for all of you, we have also a large number of emerging applications, starting from smart grid, smart farming. We are talking about smart cities, where some of them have been already deployed. We are talking about platform for telemedicine, autonomous driving, also it's coming. Now blockchain, it's already has been implemented by some governments, for example in Dubai. So the amount of information is going to be tremendous, and the number of devices also is going to be extremely terrific, that no network can handle this flood of information. So how can we handle this terrific amount of traffic, amount of network traffic? Here I want to highlight something that really we need some revolution to the current broadband wireless network infrastructure to overcome all these challenges. And I think, in my opinion, the only solution is to come up with intelligent and self-sustained radios and network elements, so they have certain cognitive function to mimic and learn the environment without the action or intervention of humans. So here I have highlighted what are the main expectation of 5G is the ability to handle 10,000 or more users call and traffic data than the current existing networks. Download speed, it's hundreds more than the current 4G networks. Connection of hundreds of thousands of simultaneous wireless nodes. We need to improve the spectrum utilization, not spectrum efficiency, in terms now of bits, hertz per unit area. Extreme data rates, more than gigabit per second, extreme capacity, finest quality of service. And in addition to the general interactive multimedia, voice, streaming, video, internet, and other broadband services that can be provided. So the requirements are huge. So in addition to the massive Internet of Things and the enhanced mobile broadband, we need to have also the mission critical control. This is a slide from Qualcomm Technologies. Actually, it's an old slide of 2016, but here it highlights all the possible requirements that are needed for the coming 5G, fifth generation networks. So what are the open issues and trends? That the main thing that emerged are due to this heterogeneous multi-layer networks, the full duplex communication, energy harvesting, and network virtualization. Actually, our previous speakers, they have elaborated quite well related to the machine learning, and actually Jacob, he raised up and mentioned that we don't have really a breakthrough in machine learning in telecommunications. However, I think machine learning has already proved itself in areas like social behavior analysis, economic and project management, computer vision, image recognition, speech recognition, for the natural language processing, also for biomedical engineering. Here I want to highlight one thing that, for example, MIT, they put some ECG benchmark data sets, and there are a lot of breakthrough to predict heart failure by spotting the wrong beats of ECG signals. From here, that's also Jacob raised up the issue that we don't have realistic data to resolve telecommunication problems. So increasing popularity of machine learning are gaining now attention in telecommunication area. So many researchers are already diverted to the machine learning new trend to resolve our current existing problem. Here I have a nice graph showing the connection of machine learning to optimization, but in terms of data analysis. And what I want to highlight here, for example, if I have certain data sets, as you can see here, so machine learning for data analysis is going to basically try to, okay, here I have different type of data sets, and the machine learning through data analysis will cluster them in depending on some well-defined feature. So when we talk about optimization, we are talking to select the best elements from a set of alternatives or trials under certain criteria. So the criteria has to be given. However, when we talk about connection of machine learning to optimization and learning, so we need the training data set, so benchmark, where we are going to train the machine, and then through some optimization based on certain criteria, and then in order to come up with a trained model. And this trained model will, by giving for any input, so the model will directly give us so if I input a car, the model will learn by itself, it's intelligent, to tell you that this is a car. So here I have a bottom-up view of classical machine learning models. So for our network problems, so for the fifth generation network that we are planning to design, the data processing, it comes from the different attributes actually within the network that can be at the mobile site, at the cell site, or provided by the network data. So we need to have these benchmark data, which are simply some attributes. We need to select the best attributes, okay, in order to come up with some features, data feature vector per samples. And then after this data representation, we need to make representation pre-processing of these extracted features, and then to build up a model selection for training. So this is the bottom-up classical machine learning models.
Excuse me, just to let you know, I know you have 44 slides.
I'm going to speed up.
No, yeah, just maybe concentrate on the...
Yeah, I know I am standing between you and the lunch time, but I'll try to speak just as a hint. Okay, thank you so much. So basically what we need to do, so our different network elements, they should be smart, they should be intelligent. So what we need to do, we need to have some machine learning decision to solve the 5th generation challenges. So here I have some graph showing all those expected challenges coming from the 5G networks. So we have exploring traffic data, we have explosive growth of network devices, some challenges related to energy efficiency. We need to come up with devices at low cost. So basically, we need to embed certain intelligence to every element within the network, also to the radios that we are planning to design. So here I have a complete picture of the next generation 5G network that should interact with IoT, with the big data, with the cloud, and then with the SDN. And this has to be augmented by the machine learning tools that we are trying, or algorithms that we are trying to design. So basically, we are generating a huge amount of data from the devices. These devices will generate the big data. So we need to do some data analytics. And then the cloud will be used to store this amount or different type of data. We need here some mobile computing power in order to do this data analytics. And then from there, we need to define or to come up with the software organized network to resolve all those challenges. So to make it brief, so basically most of the machine learning algorithm for 5G can be classified in 3 different modes: supervising, or unsupervised, or reinforcement mode. Here I have highlighted the different application with respect, for example, the regression model, KNN and SVM application for 5G can be used for massive MIMO channel estimation and detection, for user location and behavior learning. Also, we have the Bayesian learning application in 5G that are used for the channel estimation, for spectrum sensing, detection, and learning in cognitive radio. And also, the deep learning application are used for anomaly detection, flow aggregation, application identification. For the unsupervised, we have the k-mean clustering application in 5G that are used for small cell clustering, for the Wi-Fi association, device-to-device user clustering, and heterogeneous network clustering. Also, we have the PCI and ACA application for 5G for spectrum sensing, anomaly, fault, intrusion detection, and signal dimension reduction. Also, we have this reinforcement learning, where we use Markov process model for decision making under unknown network conditions. Also for channel selection and spectrum sharing, for device to device, for energy modeling and energy harvesting, and for the heterogeneous network selection and association. So I'm going to skip some of the slides which are related to the different application. So here we have a machine learning solution for estimating and predicting radio parameters. Also, we have some machine learning solution for by exploiting the trained data. So the SVM model was trained for the estimation for the channel statistics. Also, this supervised learning tool can be used for to find the optimal handover solution for this heterogeneous network that we are using. They can be also used for energy efficiency, for calculating the configuration to be used for specific location and times in the network. Machine learning also can be used for channel parameters of the desired links in the target cell, as well as those of the interfering links of adjacent channel. For example, here we are going to the pilot contamination problem encountered in massive MIMO system. Another challenge related to detection of primary users, supported by multi-antenna assisted cognitive radio networks. So also the supervised learning can be used for traffic control and optimization. So here, if you are putting certain data, we have an in-network deep learning that will give us certain data output related to application identification, service classification, fine-grained network slicing, for anomaly detection, anomaly prediction prevention, for the flow aggregation, optimal assignment of resources. K-mean clustering. So clustering is common a problem in the 5G network, especially when we are dealing with a heterogeneous network. So the machine learning solution with K-mean clustering can do such, can resolve this issue for this heterogeneous network. Another, okay, Markov. So, okay, I will skip some of the slides since I will be running out of time. I'll go to some channel learning using the machine learning. So here I have some graphs showing by learning from the past channel state information and location information. If you are using some single neural network and the multi-neural network, here we can minimize the error with respect to traditional Armax and pixel mean. As you can see here, we have quite good improvement in terms of error minimization. Another channel learning model that has been derived in reference 5. So predict the unobservable channel state information from the observable channel state information. And here you can see by using the neural network, we can obtain an accuracy of 73% compared to the random selection or the KNN k-nearest number, which gives around 50% accuracy. Quality of service prediction also can be one of the application. So we can make throughput prediction in cellular network. In the traditional methods, usually are based on counter and call traces of a live network. So machine learning based approaches, there is the ARIMA, which is a progressive integrated moving average, generalized linear model, and the random forest neural network models. Also, we have done some contribution related to the multi-layer perceptrons. So here I have certain results. The first one is comparing the network throughput prediction using ARIMA and the machine learning model. So we have pretty good match, even for weekend, few days and for during the weekend. The second table shows or compare the different, so also GLM and RF, they provide really excellent results. So accuracy goes up to around 95%. For the quality of service prediction, so we have done some simulation and generated certain benchmark data from the raw traces acquired through simulation of network sniffing and network sniffing. So here, so we have used the multi-layer perceptron, and we obtained these are the results when we use static data sets. So we have pretty good match, and we compare this calculating the mean square error and the R square. So we obtained really excellent match from the synthetic data sets. We have done this prediction using real data sets that we have already also published this type of data. So we obtained also an excellent match and very good accuracy while using these multi-MLPs. Another application of the machine learning can be used for the localization. So accurate location information can be useful for several applications, including scheduling, topology control, power control, handover prediction, proactive caching, load balancing, network planning. So here there is one nice contribution using the hierarchical support vector. So where they obtained almost 100%, and you can see here these are the simulation results coming from this contribution. So the accuracy basically decreases by increasing the variance of user locations. Another application of machine learning for the relay selection. Here we have relay selection using the ANN and SVM algorithms or models. So reduced node discovery time by 29%. And SVM, as you can see from the upper graph, shows high accuracy and less error. So this is another application. So in summary, so the different type of application can be classified depending on the modes of the machine learning that is used. Here I did not highlight about the complexity. So actually, depending on the amount of data sets, the mesh and if you are using deep learning or not, so the complexity really can be huge, and we may not have a real-time system. So the major challenge in unavailability of benchmark data sets. So most of the published work usually make use of synthetic and generated through network simulations. Simulation data typically pose high accuracy on machine learning models, and which might not be true when we are using real data sets. We need to come up with a standardized method and should be established to acquire real network data. The other challenge is the data representation. So common method to represent network attributes in data sets. Is the representation equally significant for the different machine learning algorithms? So evaluation of machine learning methods over benchmark data sets. Also performance versus complexity trade-off. New context specific metrics need to be defined to evaluate the machine learning algorithm performance rather than traditional metrics such that the root mean square error, precision, etc. So at the end, so machine learning cognitive radius and SUN. So machine learning based algorithm for network optimization need to be implemented in software defined radio and cognitive radio architecture to enable self-organizing networks. I think this is will conclude my talk, and if you have any question, I'll be happy to answer. Thank you.
Thank you very much. So we are 10 minutes behind time. I'm not here today, but maybe we have one urgent question. Otherwise, yeah.
One question regarding the localization accuracy. We saw the probability, the accuracy probability on the y-axis, but what is the accuracy in meters? What does it mean? For which accuracy it has been investigated?
Actually, in the contribution that has been published, he used just the variance with respect to the location. So he did not provide exactly. So that's not my own contribution.
Good, thank you.
Okay, yeah, please.
So at which layer you apply machine learning? Layer 1 physical layer, or layer 2 or layer 3?
Actually, for the contribution about in the MLP that we have done, so basically we just collected or provided some benchmark data sets, and we used the log traces to get the different attributes from the network. So basically you can, from the log files, so this is the attributes existing within the network. So I think from, not only from the physical layer only, so you used, for example, the single strength indicator. We have used so many other attributes that can be from the network, also from the physical layer.
But what I meant is the machine learning algorithms themselves are executed in the physical layer, or layer 2 or layer 3, or network management or control plane, where machine learning or deep learning algorithms are executed.
So the machine learning algorithm can be, so what should be done in the future, the machine learning or the intelligence should be embedded almost everywhere, at the device side, at the network side. So it's not only, this is what I think that will be the most practical and the most intelligent system that we want to design or come up with.
So my last question, So far I have seen the discussion about using machine learning for wireless. Can we use it in Ethernet?
Can we use it in?
Ethernet. Like in front hole, back hole, mid hole. You can use Ethernet for transport.
I'm not expert on that, but I will leave the floor for the expert on to answer this question. Thank you.
Maybe during lunch then. Thank the speaker again. Yeah, it's time for lunch. I think we should meet 2:20. Does everybody know where to get lunch?
Just follow everyone else.
Okay, yeah. Follow him. Okay, see you.
So it's about 30 meters from here. There is a cafeteria. So you exit, and then you turn right, and then about 30 meters to your right is a cafeteria.
Okay.
It's actually good that they're a bit late because it's quite crowded today. So you will have not a big queue now, I think.
Nice talk.